Hi, here we are going to discuss chemistry part of ReNEET 2026 and we have taken the code 50. Okay, the first 45 questions are from physics and 46th question onwards is from chemistry and the very first question, that is 46th question, is from organic chemistry, probably from the chapter aldehydes, ketones and carboxylic acids. Okay. And the question is this. For the reaction sequence, choose the correct option. And they have provided with a reaction sequence. It is benzene treated with two sets of reagents. First one, acetyl chloride and aluminum chloride. Then probably anhydrous aluminum chloride. That's not mentioned there. And second one is sodium hypochlorite. And there are two products which are denoted as P and Q, P plus Q. And the options are regarding P and Q. What are the options? We will check. First one. One is the answer. If P is sodium salt of a carboxylic acid and Q is an alcohol. 2. If P and Q are aromatic compounds. 3. If P gives a carboxylic acid on acidification and Q gives a poisonous gas on exposure to air and light. And lastly 4. If both the P and Q are carbonyl compounds. This is the question. Okay. Now we will see what we know these reactions. Both these reactions are familiar to us. Look here. Benzene upon treatment with the acetyl chloride and aluminum chloride. We know treatment with the treatment of benzene with acyl chloride in the presence of a Lewis acid like anhydrous aluminum chloride. Acylation takes place and that reaction is called Friedel-Crafts acylation. And what is the result? A acyl group is introduced onto the benzene ring. COR group is introduced from RCOCl. Okay, here it is particularly CS3COCl. So the introduced group is CS3CO. So we have this product, a aromatic ketone, which is known as acetophenone, or methylphenyl ketone or phenylethanone. Okay, that's the product. That's the first reactant. What's the second one? Sodium hypochlorite. See, we know that when methyl ketones are treated with either sodium hydroxide and chlorine or sodium hydroxide and bromine or sodium hydroxide and iodine or sodium carbonate and iodine, etc., we know two major things happen. First thing is that the hydrogen atoms there get replaced by 3 halogen atoms. Okay, that part is getting oxidized because hydrogen is replaced by chlorine atom. And the next thing is that it gets cleaved beyond CO group. So one part become sodium salt of the acid and the other part become a haloform. If you are taking chlorine, you get a chloroform, CHCl3. Okay, so in this second part of the reaction, one more thing, here we have chosen NaOCl. Instead of taking NaOH and Cl2 separately, we can take a sodium hypochlorite. Effect is the same. Sodium hypochlorite, sodium hypobromate, etc. So here we have chosen sodium hypochlorite, and what happened? The molecule has been oxidized and cleaved so that the one of the product is sodium benzoate and the other product is chloroform. These are P and Q, not the final products. P and Q are the immediate products. And what they further say, P on acidification gives a acid. Yeah, it is correct. Sodium benzoate gives benzoic acid on acidification, correct. And what the other thing, what is mentioned about Q? They say that Q upon exposure to oxygen in the presence of sunlight gives a poisonous gas. We know that. Chloroform upon long standing in the presence of oxygen and in the presence of sunlight gives the poisonous gas phosgene. That's why old samples of chloroform is not recommended for anesthesia because this poisonous gas can kill the patient. So these are the final conclusion. So going back to the options given, look into the options again. What's the first option saying? If P is the sodium salt of carboxylic acid, that part is correct. If P is the sodium salt of the carboxylic acid, Q is an alcohol. That's wrong. So 1 is not the answer. If P and Q are aromatic compound, that's also wrong. Only benzoic acid, sodium benzoate is a aromatic compound. The other one, chloroform, is not an aromatic compound. So 2 is not also not the answer. If P gives a carboxylic acid on acidification, Q gives a poisonous gas on exposure to air and light. That's true. So our answer must be 3. And lastly, if both the P and Q are carbonyl compounds, wrong, because chloroform is not a carbonyl compound. So we come to the conclusion that 3 is the answer for our first question. Okay. Next question, 47. Given below are two statements. Statement 1. FeOX thrice 3 minus is chiral. Statement 2. Trans CrH2O twice OX twice minus is chiral. Given OXH2 is HOOC COOH, means oxalic acid. So in the question they mean we have oxalate ligands, bidentate oxalate ligands. Okay. In light of the above statement, choose the most appropriate answer from the given options below. Both statement 1 and statement 2 are correct. Both statement 1 and statement 2 are incorrect. Statement 1 is correct, but statement 2 is incorrect. Statement 1 is incorrect, but statement 2 is correct. See, so this question is from coordination chemistry. Coordination chemistry. And it is purely based on isomerism shown by complexes, the geometrical and optical isomerism shown by complexes. In this particular case, it is regarding octahedral complexes. So, we have to discuss in detail what really happened here. Then we come to this question's answer. Okay? Octahedral geometry results in complexes either through D2sp3 hybridization or sp3d2 hybridization of the central atom or ion. Okay. We can visualize this octahedral structure as imagine the Cartesian coordinates x-axis, y-axis and z-axis, and also imagine you cut at equal distance from the center along all the axes on either side of each axis. Then you will have 3 mutually perpendicular lines like this, isn't it? If you have the central metal atom or ion at the origin and the ligands at the edges, then we have the octahedral geometry. See, there are only 6 ligands, yet the structure is not hexa but octa, because octahedra means 8 faces. Why? See, such a structure leads to octahedral geometry. Why? What is this meant by this octahedron? 8 faces. How they are developed? See, if you connect all these edge atoms, 1 triangle, 2 triangle, 3, 4, below another 4, making 8 faces out of 6 bonds. That's why there are only 6 bonds but 8 faces for the structure. That's why it is called octahedral geometry. Okay, remember that. Now, imagine the molecule is having all the ligands identical, and we can represent that as Ma6. A is the ligand, all are identical, like this, Ma6. In this case, you cannot have a geometrical isomerism. Why? By exchanging the positions of any two ligands, you are not going to get a new variety in this structure. By exchanging any 2 ligand, you are not going to get any new variety, because there is no, you have to remember, don't think this is axial and these are equatorial. All are identical. Now the equatorial become axial and axial become equatorial. So all are identical. So there is no exchange that resulting in a new variety. So we can say that Ma6 doesn't have geometrical isomerism. Now think about optical isomerism. For optical isomerism, you have to take the mirror image of this structure, isn't it? If you show it in front of a mirror, it will be like this, isn't it? And suppose the mirror image gain life and come out of the mirror, they will be exactly identical and superimposable like this. Okay, so we can say that Ma6 molecule doesn't have either geometrical isomerism or optical isomerism and can exist only in one form. Now we can start introducing bidentate ligand. Replace 2A by a BB molecule, BB ligand like oxalate ion, diethylamine, etc. Not diethylamine, ethyl diamine, etc. Then what happened? Suppose you introduce a ligand, say like this. Replace one of the structure with a bidentate ligand. That's what you are doing now. In the model, we do it like this. Okay, sorry. Like this. One of the two ligands A were replaced by a BB ligand. Okay. Even now, this molecule does not have geometrical isomerism. You know why? All the pair of ligands at 90 degree are identical. Whether you place it here or place it here or place it here or anywhere in this molecule, you get only one variety. So you don't get a geometrical isomer for Ma4B2 type molecule. Has any possibility of optical isomerism? No. Why? Because this molecule, if shown in a mirror and the mirror image comes out, it will be exactly identical like this and superimposable over this. The mirror image will be like this. On sliding, it will exactly superimpose with this, irrespective of the position of the bidentate ligand. Okay. The reason is why it has no optical isomerism, we can say in another way also. It is a plane of symmetry like this. It is a plane of symmetry like this. Okay, there are two or more planes of symmetry which divide the molecule into two identical halves. So what happened? It's whenever there is a plane of symmetry, the object form will be superimposable on the mirror image. That's the rule. Whenever there is at least one plane of symmetry, the object form and mirror image form will be identical. What happens is that object's right side superimposes with the left side of the mirror image. Object's left side superimposes with the right side of the mirror image because these two are identical. So there is no optical isomerism too. So our conclusion about Ma4B2 is that, I will repeat for the first one, for Ma6 there is no geometrical isomerism. Since it has a plane of symmetry, it also has had a plane of symmetry, it has no optical isomerism. Coming for the next case, Ma4B2, it is also having no geometrical isomerism. Since it is also having a plane of symmetry, it also does not have optical isomerism. Okay, two cases over. Now we replace one more pair of A with another BB. Means Ma2BB twice. Ma2BB twice. Okay, we will see that. See here, it has two possibilities. What are the two possibilities? See, if I connect one BB like this, I can connect the next BB on exactly opposite side of it, above and below. It comes on an Hindu mark of 4 ligands, one above, other below, and one ligand towards you, A towards you, one A towards me. Okay, so this is one form. It is called trans because the two ligands, bidentate ligand are on opposite sides. Since bidentate ligands are on two opposite sides of one of the plane, it is called the trans form. See, the transform has a plane of symmetry like this. It can be cut like this. It can also be cut like this into two identical halves. Since it is having two identical halves, it does not have what? It does not have optical isomerism. I will show you. This is its mirror image. Look here. It's a mirror image. Will be exactly like this, no? Okay, there is slight difference in the making. Otherwise, they are exactly similar. So they will superimpose, whereas the bidentate ligands as well as the monodentate ligand exactly superimpose on one another, because it has a plane of symmetry. That's why it has no optical isomerism. So coming to the case of Ma2Bb twice, it has two forms, of which one we have discussed, which is the transform, where it has a plane of symmetry and object form and mirror image form are identical with one another, so it does not have optical isomerism. Now it has another, when there are two bidentate ligand, another possibility is also there in addition to the transform, which is the cis form. How? Look here. Once I place one BB ligand like this, the other I should place on any other pair of ligands other than that on the opposite. There's only one opposite pair. I leave that and instead I ligate like this in another plane. This is in one plane, this is in another plane. Look here, this is in another plane, isn't it? This plane. This is in this circular plane, this is in this circular plane. What happened? This is the form. It is called a cis because they are not trans as in the previous case. Remember, in the trans, they are opposite to one another. The two red ligands shown by that wire are on opposite sides, whereas it is not on the opposite side. Okay, this is the cis form. See, so remember, Ma2Bb twice has geometrical isomerism possible. First case where geometrical isomerism arose so far. And out of this two geometrical form, one is trans, it had no optical isomerism, whereas now we are dealing with the cis form. It has no plane of symmetry. You cannot divide this molecule into two identical halves. That's the specialty. You cannot divide this molecule into two identical halves. If you cut like this, you know both halves are not identical. If you cut like this, then also it is not possible. In whichever plane you desire, you can cut it and you are never going to get two identical halves. So it's a mirror image. It's a mirror image. Look here. This is, now you can see these are object and mirror image, isn't it? Look. Facing each other. The other two also facing each other. They are mirror images. Try to overlap them. You will never possible. You can, it is difficult to show with this model. You can never superimpose in whichever mode you try. They won't superimpose. They won't superimpose. Anyway, if the models are with you, you can easily try it. You will see that they can never superimpose on one another. And so, cis form lacking a plane of symmetry shows optical isomerism. So, we can conclude about Ma2B4. B4 means BB twice. Ma2BB twice has two geometrical isomers because it has two distinct forms which were trans and cis. Trans has had a plane of symmetry, so no optical isomerism. Whereas cis does not have a plane of symmetry, so had optical isomerism, two distinct forms. Okay, only one more is now remaining to be discussed, which is MBB thrice. All the three are bidentate ligands, making the total ligation 6. All A are replaced by BB group. Okay. Yes. Look, you never make a ligation in the opposite sides. All the three are cis linkages, 90-degree linkages like this. Look, we can imagine, see, the structure has the specialty that, look here, I'll explain. These edges of the octahedral geometry actually lies in three circles. One circle this way, other circle this way, third circle this way. Three mutually perpendicular circle we can imagine, and this basic structure remains within that three mutually perpendicular circle because they are, the molecule itself is in three planes. One plane, another plane, third plane. Here the ligation, these red wires are lying in three different circles. Look, this ligation lies in this circle. This ligation lies in this circle. Agreed? And this ligation lies in the third circle. In that structure, remember, it is very clear that it does not have any plane of symmetry. You can't ever cut it into two identical halves. Okay? You cannot cut it into two identical halves. And it's a mirror image. It has no geometrical isomerism. Okay? It has no geometrical isomerism. It's a mirror image will look like this. See, one red here, one red there. Two reds here and the remaining two reds. If you verify, look, you can see they are mirror images. You can't ever superimpose one on the other. This is distinct. This is distinct. In which way they are distinct? One is the mirror image of the other because they don't have plane of symmetry. That's much. This gives the full explanation for our next question's answer. See, so our last conclusion, B2 thrice type molecule, B2 thrice type molecule has no geometrical isomerism shown. Further, the molecule has no plane of symmetry, and so object form and mirror image form are non-identical. So it shows optical isomerism. Okay. Now we can easily answer our question. Okay. We will see how we answer the question. Okay. Okay. See, before answering this question, we can make a conclusion. See, MO6, we have seen no geometrical isomerism, has no plane of symmetry, has plane of symmetry, so no optical isomerism. MA4BB means one bidentate ligand introduced, same explanation, no geometrical isomerism, has plane of symmetry, no optical isomerism. Now, two bidentate ligand, MA2BB twice, has GI, which are they? Trans and cis. Trans has plane of symmetry, no optical isomerism. Cis, no plane of symmetry, has optical isomerism. Has POS, no OI. No POS, has OI. Finally, MBB thrice has no plane of symmetry. So, has optical isomerism. Of course, it has no geometrical isomerism. These were the conclusions we have drawn. Now we come to the question back. Look here, statement 1. FeOx thrice 3 minus is chiral. See, what is FeOx 3 thrice minus means? It means 3 bidentate ligands. This means 3 bidentate ligands. First statement involves a bidentate ligand. Bidentate ligand like this. We know bidentate ligand has no plane of symmetry, so has optical isomerism. When a molecule does not have a plane of symmetry, it is chiral, isn't it? So chiral means no plane of symmetry. So statement 1, FeOx thrice 3 minus with the 3 bidentate ligand is chiral is a correct statement. is a correct statement. Got that? Because it is about a molecule of the type MBB thrice. So it is chiral, that is, it has no plane of symmetry. It is correct. What about the second statement? Statement 2. Trans Cr H2O twice OX twice. See, it is similar to what? It is similar to this molecule. This molecule. Which one? Transform. Two opposite sides by dentate ligands are arranged. It has plane of symmetry. It has plane of symmetry. No optical isomerism. We remember. We have explained it in detail. Isn't it? We have explained it in detail. So, it is achiral. It is not chiral. It is achiral means it has no plane of symmetry. It has plane of symmetry. I'm sorry. It has plane of symmetry. So, it is achiral. So, statement 2. Trans Cr H2O twice. 2 bidentate ligand, 2 monodentate ligand. Here, monodentate ligand towards you and me. This and this opposite side. They are H2O molecule. The other two are oxalate molecule on either side. Okay. So, it is transform. It has plane of symmetry. So, it is achiral. It is not optically active. It is achiral, whereas it is given here as chiral. So, that statement is wrong. So, statement 1 is correct. Statement 2 is incorrect. Option 3 is the right answer here. Option 3 is the right answer here. Hope you understood that clearly now. Okay. Hi, the next question number 48. The following carbocation is stabilized by the interaction of the empty p orbital with. That's the question. This question can be said to be either from chemical bonding and molecular structure or from basic principles of organic chemistry. It includes ideas from both chapters. See, this is the structure they have given. What it is? It is a carbocation obtained from ethyl benzene by removing the hydrogen as H minus from the carbon which is directly attached to the benzene ring. It is removed as H minus so that one plus charge comes over there. Okay, this carbocation, how it can be stabilized? Look, it is this structure I have drawn in yellow color, and that is the empty p orbital. Thus, plus charge suggests the absence of electron there. Okay. See, it can either conjugate with one of the pi bond in the benzene ring where this shifts over this as I shown by the green arrow. Then what? The resultant structure, it will be the resultant structure. Double bond here, HCS3, and plus charge migrate to the next position of the benzene ring. It comes into the benzene ring, the plus charge. So that way it can get delocalized to the left side. At the same time, it can get delocalized over the other side. How? One of the CH sigma bond can be shifted over here so that a double bond comes here. Okay? And that H who lost the pair of electron remains as an H plus in the vicinity. It remains as there. It is called hyperconjugation or sigma pi conjugation there. So the red line change is shown and the resulted structure is shown here. Okay. So it can either collect this pair of pi electron or collect this pair of sigma electron. So we can say that this aromatic carbocation gets stabilized either by a filled sigma and a filled pi orbital. Filled sigma is this and filled pi is this. So our what are the options given? Filled sigma and filled pi orbital, empty sigma and empty pi star orbital, empty pi sigma star and a filled pi orbital, filled sigma star and a filled pi star orbital. Here the pi star sigma star antibonding orbitals doesn't come into our explanation or picture. So our answer very clearly the first one, filled sigma and filled pi orbitals. Okay. The next question number 53. See, among the following options, the correct trend in electron gain enthalpy. So this question is said to be from periodic properties, +1, okay, 11th standard. Now, among the following option, the correct trend in electron gain enthalpy, fluorine greater than chlorine greater than bromine greater than iodine, bromine greater than chlorine, like that. We know that electron gain enthalpy released is more for fluorine than, more for chlorine than fluorine. This is because, as we know, in the case of fluorine, the incoming electron is slightly repelled by the tight electron cloud of the small fluorine atom. And as a result, the energy released by fluorine during the capture of electron is slightly lesser. For that reason, electron gain enthalpy, which is the enthalpy change during capture of an electron by an isolated atom, gaseous atom, that is maximum for chlorine, then for fluorine, then for bromine, then for iodine. See, while we talk about the order, you have to remember that here they didn't mean to consider the sign, because all these values are negative. A big negative value is actually a small value, but that is not the way to conclude here. The questioner didn't suppose us to think that way. The one who said the question didn't mean us to think that way. We shouldn't think the mathematical aspect. The general way of telling is that the electron gain enthalpy of chlorine is high. Actually, it would have been better if they say the electron gain enthalpy released follows the order, but they didn't say like that. They simply said electron gain enthalpy follows the order. So don't get under the impression that we have to consider the sign here. We don't have to consider the sign here. They actually mean the quantity only. They meant the quantity only, and for that reason the order will be chlorine greater than, fluorine greater than, bromine greater than iodine. Their values are in our textbooks. 11th standard textbook, the value of chlorine is minus 349, fluorine is minus 333, bromine is minus 325, and iodine is minus 296. Okay, so the order chlorine greater than, fluorine greater than, bromine greater than iodine. Remember that. Okay. Next question, 54. Assertion reason. For an ideal solution formed by mixing liquid P and Q, delta H mix, the delta H mix is equal to 0, delta V mix is equal to 0. Okay, that's the assertion. And the reason? No interaction occurs between P and Q. See, in the previous last year's exam, there were no assertion reason type question, only statement 1, statement 2. In assertion reason type, the problem is that we may get confused between option 1 and option 2. That is, whether the reason justify the assertion or not. There sometimes some confusion arises. But here in this particular case, even though the question is of assertion reason type reintroduced, there is no such a confusion. See, reason is what? No interaction occurs between P and Q. We again read assertion A. For an ideal solution formed by mixing liquid P and liquid Q, delta H mix is 0, delta V mix is 0. That's correct. Since the total interaction doesn't vary between the two substances mixed up, there is no total change in the attractive repulsive forces among the molecule even after mixing. So that delta H mix, there is no enthalpy change, heat is neither gained nor lost, nor there is a change in volume. That is, if you mix 300 volume of one liquid with 300 ml of 1 liter liquid with 200 ml of the other liquid, the total volume will be 500 ml. It will not become 499 or 501. Okay. So delta H mixing and delta V mixing is 0 for ideal solution. Okay. Then what is the reason given? No interaction occurs between P and Q. That's wrong. Interaction is there, but that interaction is as equal to the interaction before the mixing of A and B. Total interaction of it does not change, so that there is neither gain of energy nor losing of energy. Okay, that's why it is happening. So we can say that reason is wrong. Reason should not have been like this. Reason should have been the total interaction energy, total interaction effect does not change. That is the actual reason. So the given reason that there is no interaction at all between P and Q is wrong. Okay, so the answer is assertion, true, correct assertion, wrong reason. 3. Option 3. A is correct, assertion is correct, but R is not. Hope you understood that. Okay. Now the next question. The amino acid that gives a red blood color on treating its sodium fusion extract with the sodium nitroprusside is. See, the question is from 11th standard. Basic principles, some basic principles of organic chemistry, elemental detection. See, if the compound, if it is an organic compound, it is supposed to already contain carbon, and if in addition it contains nitrogen and sulfur in the sodium fusion extract, that is when the compound is strongly heated with the excess sodium metal, sodium thiocyanate ion may be formed. Thiocyanate ion SCN minus can be formed. Should not take too much excess. In that case, they will split to sodium, cyanide and sulfide. If you take moderate amount of sodium thiocyanate ion will be formed, SCN minus, and when it comes in contact with the Fe3 plus ion, it will form FeSCN2 plus ion, a complex ion. FeSCN, both in a bracket with the 2 plus charges remaining. 1 plus charge cancels. That ion has a red blood color. So we can conclude that amino acid which has carbon is always there, that amino acid which nitrogen is also there because it is an amino acid. So that amino acid which is also having sulfur will give a blood red coloration in the sodium nitroprusside when treated with the sodium nitroprusside. Okay, so our answer is we have to choose from leucine, threonine, methionine and serine. This also this question also tells you one thing. You have to be familiar with the structures of all the amino acids given in our textbook. The 20 amino acid structure you have to remember, otherwise such question cannot be answered. Okay, so our answer for this question is methionine because it contains thioetheric linkages. See, I have a doubt whether it is clear in the since the background of the image is white. I am not sure whether you can see it clearly. It is methionine. It is having CS3S CH2 group in the place of R group. When amino acids are generally represented as R NH2 COOH R CHNH2 COOH. That R group in this particular case of methionine is ethyl methyl ether, ethyl methyl thioether, where the ether part is attached to the amino acid part. This is the molecule. Okay, so methionine is the answer. If you go through the structures of leucine, it is having an isobutyl group in the place of R. In the case of threonine, you have an ethyl group along with an OH group. So that is also not the answer. And in the serine, you have a hydroxymethyl group. All these are not containing sulfur. Only methionine is containing this sulfur. So blood red coloration can happen only in the case of blood. See, my face is not clear there. That is not at all a problem. So methionine is your answer. Okay. Next question. The standard electrode potential E0 for the half cell reaction Fe3 plus E minus giving Fe2 plus at 298 Kelvin. For that you are given the E0 values for two other reactions of Fe3 plus bar Fe and Fe2 plus bar Fe. See, in such problems, how you can get the answer? The first thing is that you have to write the full equations for the given equations as well as the equation whose answer has to be found out. Look here. What is the required equation? That you have to write first. Listen carefully. The required equation is Fe3 plus E minus giving Fe2 plus. its voltage we have to find out. We mark it as E01. What are the given equations? Fe3 plus 3E minus giving Fe. Ferric ion become iron atom. Its voltage is given minus 0.04 volt. Okay. And the third next equation given is Fe2 plus 2E minus giving Fe. The two given equations are ferric ion become iron atom and ferrous ion becoming iron atom. The voltage of both are given. If you verify equation 1, 2 and 3, you can see that equation 1 plus 3 after some cancellation gives equation 2. Chemical equation 1 plus chemical, you can verify, chemical equation 1 plus chemical equation 3 will give you chemical equation 2 after the cancellation of Fe2 plus, which is common. So what result will be equation number 2. Okay. If that is the case, as in thermodynamics, when two equations are added, there we add the enthalpy changes also, isn't it? Here we cannot directly add the voltage values like enthalpy, because enthalpy, voltage values are not additive. Instead, free energy changes are additive. For a particular cell, its delta G values are additive. So what are the delta G values? We know delta G is equal to minus NFE. Is an equation we study, isn't it? So in the place of delta G standard, delta G1 standard plus delta G3 standard is equal to delta G2 standard. We substitute N1F E1 standard plus N3F E3 standard giving N2F E2 standard. Got that? Then now you substitute. If you look at the equation, from where you get N1, N2 and N3, these are nothing but the number of electrons involved in that particular equations. Okay. N1, N2, N3 are the number of electrons involved in this equation. So if F is common, it cancels off. So what remains? N1 E01 plus N3 E03 giving N2 E02. Okay. Substitute. Then you get, after simplification, you get a 0 plus 0.76 volt is the answer. Plus 0.76 volt is the answer for this particular question. Okay. That is option, which one? Option 2 in the among the given answer. Okay. Hope you understood that. One more problem. Next. In an acidic medium, 10 ml of 0.25 molar oxalic acid is titrated with a KMnO4 solution. If the volume of KMnO4 solution required to reach end point is 10 ml, the strength of KMnO4 solution is. Listen, it is a case of some kind of neutralization. It is not acid-base neutralization. It is actually oxidation reduction, redox reaction. See, whether it is acid-base neutralization or a redox reaction between oxidant and reductant, the thing you have to remember, at the end point, number of equivalents of one reagent will be number of equivalent of the other reagent. Okay, number of equivalents of one reagent will be number of equivalents of the other reagent. How number of equivalents is obtained? It is normality into volume. Number of equivalents is normality into volume. Now, if it is given as molarity, you have to convert molarity into normality. You have to remember, for oxalic acid, 1 molar is 2 normal because it is a dibasic acid. Again, KMnO4, 1 molar is 5 normal. That you know from several, even theory as well as from practical. You know that what I am not going to enter into its detail. 1 molar because every 2 mole of KMnO4 release 5 mole of nascent oxygen. 2 mole KMnO4 release 5 mole nascent oxygen. That means 2 mole KMnO4 is 10 equivalents because 5 mole O is 10 equivalents. So 2 mole KMnO4 is 10 equivalent. So 1 mole KMnO4 is 5 equivalent. That's why it's a molarity 5 normal. 1 molar is 5 normal. So to convert the given molarity to normality, you have to multiply with the 5. So here what we do, NV oxalic acid is equal to NV KMnO4. That is what we have to remember. Okay. Suppose listen carefully. Here oxalic acid normality N is equal to 2m is equal to 2 into 0.25. Okay, so it is 0.5 normal. In the question it is given the molarity of the oxalic acid, which you convert to its normality by multiplying with the conversion factor 2. Again, for KMnO4, 5 molar is equal to 5 into x, where x is the molarity. For KMnO4, normality is equal to 5 molar. So 5 into x, where x is the molarity of the KMnO4. Potassium permanganate molarity you have to find out. Okay. Then at end point, NV oxalic acid is equal to NV KMnO4, isn't it? So what is NV KMnO4? NV oxalic acid 0.5 into 10 is equal to, for KMnO4 how to substitute 5x into 10, isn't it? NV of oxalic acid 0.5 into volume consumed is 10 ml. For potassium permanganate it is 5x into 10 because both volumes were given as 10 ml. So what x you get as 0.1 molar. Okay. So remember, you cannot, in such problem, you cannot directly use molarity always. You have to first convert them to normality. Then only the equivalents are equal at the end point. Moles are not equal. That's why we cannot use molarity into volume is equal to molarity into volume. You are supposed to use only normality into volume of one reactant is equal to normality into volume of the other reactant. You must know the conversion factor. 1 molar, how many normal? 1 mole, how many equivalent? Both are same. How many? 1 mole, if x equivalent, 1 molar will be x normal. Okay? Hope you understood that. So here the answer is 0.1. Answer 1 is there. Okay? Okay, the next question. Consider the reaction sequences and choose the correct option. C, PH, that is phenyl ring. C triple bond C, CS3. Okay? And first set of reagent, sodium in liquid ammonia, which gives you the first product L, which upon treatment with the HBr in the presence of benzoyl peroxide gives you N. The second path is reducing the same reactant with the hydrogen and palladium carbon mixture, which is Lindelois catalyst. Okay, and that gives you product K, which upon treatment with HBr, here there is no benzoyl peroxide, the product is M. Then we have certain statement regarding these products K, L, M and N. We have to choose the correct one. Okay, so we will first study the reaction. See, sodium in liquid ammonia is used to reduce non-terminal alkyne groups. Okay. See, when such a reduction is carried out, anti-addition takes place. Anti-addition, another case of anti-addition. Sodium in liquid ammonia is a reducing mixture and the addition is anti. So, one hydrogen comes from here, the other hydrogen comes from here. So you get this product. Okay, where addition happened is anti. Now you are treating that with the HBr in the presence of benzoyl peroxide. If benzoyl peroxide is present, we know that anti-Markovnikov addition takes place as a general rule. Okay, so in anti-Markovnikov addition, you know that free radical mechanism is the case, not the ionic mechanism. And see, in normal ionic mechanism, in the absence of HBr, in the absence of organic peroxide, H plus add first, Br minus add later. Agreed? H plus adds first to the double bond, then Br minus. But in the presence of organic peroxide, there are two differences. One, the addition is non-ionic, free radical. The other is here Br free radical adds first followed by hydrogen free radical. Two differences. So here, to this, when HBr is added in the presence of benzoyl peroxide, Br adds to this carbon, not to this carbon. You know why? If bromine is added over this carbon, this junction become the free radical. It is the free radical junction. And this free radical junction can be stabilized by resonance with the benzene ring, isn't it? You know, not only cationic side but even free radical side can be resonance stabilized. So preference is bromine added here and H added later here. Now in the second stage we know hydrogen gets added onto the free radical side. Okay, so Br here, H here, this will be the final product. Now you have already got 2, L is got, N is got. Now hydrogen, palladium, carbon, palladium with the carbon, which is Lindlar's catalyst, and you know that catalytic addition, as I mentioned in the previous questions, catalytic addition is always syn from the same side of the double bond. So here, as we expected, the product is like this, pH, isn't it? And HBr addition in the absence of organic peroxide, isn't it? We know again here it become cation, so that cation as well as free radical is stabilized by resonance with the conjugating aromatic ring. Okay, so H adds here, okay, so that plus charge comes over here like this. Look here, isn't it? So it can get stabilized. Later on, bromine adds over here. So the final product M is this. Now the statements are regarding L, N, K and M. You will check one by one. What is the first statement? Here, I'm sorry, this is the answer. K and L are geometrical isomers. Is that correct? K and L are geometrical isomers. We will check. K, L, yeah, this is the cis isomer of the trans variety. So K and L are geometrical isomers is a correct statement because they are cis and trans. That is correct. Only one correct answer will be there. So the other 3 are expected to be wrong. No. What's the next statement? K and L are enantiomers, optical isomers. No, that is wrong. They are geometrical isomers. M and N, next M and N are geometrical isomers. M and N are stereoisomers. Both must be wrong. M and N are they geometrical isomers? M and N. Look here. M versus N. See here bromine is on this carbon, whereas bromine here is on the carbon which is also attached to the phenyl group. So structurally they are different. They are structural isomers. There is no question of if they are structural isomers. There is no question of stereoisomerisms like geometrical isomerism or optical isomerism or stereoisomerism. You got that? So there is no doubt they are not geometrical isomers nor stereoisomers. So evidently the question number, this question has option 1 as the correct answer. That is K and L are geometrical isomers. Hope you understood that. Okay. We proceed to the next question. The complex which has facial and meridional isomers is, just a minute. Okay, what is meant by facial and meridional isomerism? See, facial and meridional isomerism is shown by octahedral complexes where 3 monodentate ligands are of one kind and the remaining 3 monodentate ligands are of other type. It is shown by MA3B3 type octahedral complexes, which here is an MA3B3 type. See, evidently Cr pyridine 3 times chlorine 3, not others. Here all are water molecule. Here 4 are ammonia, 2 is water molecule. Here 2 is ethylene diamine bidentate ligand and 2 is water molecule. And what is this facial meridional thing? Let's see. Pyridine is benzene ring where one of the CH group is removed by a nitrogen atom. It is aromatic ring where one of the CH is plucked out and N, not NH, N is placed back. That is pyridine. Okay. So, what is meant by facial? What is meridional? Look. Facial is that form in which 3A molecules are mutually, 3A ligand A is mutually perpendicular. Here let yellow be A. These three are mutually perpendicular, no? Agreed. The remaining three are B. They are also mutually perpendicular. C, orange, 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 mutually perpendicular. So, a set of two, three mutually perpendicular identical groups. Three mutually perpendicular identical group, one set, three mutually perpendicular identical group. Such structure is called a facial, F-A-C-I-A-L, facial. What is meridional? Here the difference is that the yellow set, look at the yellow set, it forms one T, letter T. Agreed? They are not mutually perpendicular. Agreed? Then what is orange? It is another T in the perpendicular plane, another T. So this is one orange T and this is one yellow T. So two mutually T is connected. So this type of structure is called a meridional. So facial and meridional are shown by what? M A3B3 structure. Here it is MPY3Cl3. Hope you understood that. One is the answer here. The next question. Yeah, diagram I have shown here. Identify the reaction which give aniline as the major product. Okay, 4 are given. We will check the answer part. There things are shown clearly. See the first reaction. Benzene nitride or cyanobenzene. If it is reacted with the lithium aluminum hydride and H2O, this CN is reduced to CH2 NH2. You get benzylamine, not aniline. Okay. That reduction gives you benzylamine, not aniline. So that's not the answer. What is this? Hofmann's bromamide reaction, hypobromate reaction or bromamide reaction. This CO goes and that NH2 become directly attached. KOH bromine, Br2 reaction. Or you can use NaOBr or KOBr assessing hypobromide. Sodium hypobromate, NaOBr, potassium hypobromate, KOBr, or use the mixture KOH and Br2 or NaOH and Br2. It is a degradation reaction because one carbon goes from the chain and NH2 get directly attached. So here we get aniline. So B is one of the option. And what about C? It is not at all a familiar reaction for us. Okay, it is called azoxybenzene. It is formed. Okay. And that what is last D? It is hydrolysis. Acetanilide. It is acetanilide, acetylated aniline. That's why it is called acetanilide. If it upon hydrolysis gives NH, here the cleavage happens. One part becomes CS3COH acetic acid and the other part become hydrochloride salt of aniline, anilinium chloride. That can be also considered as a product of aniline. So that can also be considered as an answer even though directly it is not giving aniline. Still that can be accepted as an answer. So our answer will be B and D. B and D. Even though D is not directly giving aniline. Here B and D. The questioner also meant that much only. So B and D is the answer. Option 2 is the answer. Question number 80. This is a thing to be by heart from biomolecule. See, I am not spending too much time. Vitamin is very much available from carrots. So rabbits will have a very sharp eyesight, isn't it? Because they eat so much of carrots. Vitamin B12. meat. That's why vegetarians have vitamin B12 deficiency very much. Okay, vitamin B12 is mainly from wheat. Vitamin E, sunflower oil, vitamin E. And vitamin K, green leafy vegetables. That's the correct answer or correct cross combination, which was 2. Not detailing much upon it. Now, next question. The correct decreasing order of oxidation states of underlying element. P4 or 10. So, very easy. We will straight away go to the answers. Look here. P4. Oxygen required 10 electron. 10 into 2, 20 electron. Since there are 10 oxygen atoms. These 20 electrons are provided by 4 phosphorus atoms. So, oxidation state of each phosphorus is plus 5. In SO3, 3 oxygen requires 6 electrons. So, sulfur's oxidation state plus 6. In here oxygen minus 2 because H is plus 1 H. Next, N2O5. Oxygen totally required 10 electrons. So, each nitrogen is plus 5. Al2O3. 6 electron required by oxygen, so each aluminum gives plus 3. Again oxygen minus 2. PbO2. O2 requires 4 electron, so Pb gives 4 electron. It is not peroxide, it is normal oxide. N2O3. 6 electron required, so each nitrogen is plus 3. 6 electrons, so plus 6. P4O6. 12 electron required, 4 phosphorus atoms are there, so each is 3. 7 oxygen required 14 electron, so each chlorine plus 7. ALS3, 3 aluminum provides 3 electron, so aluminum is plus 3. So, which is having a correct decreasing order? Only this is having, option 2 is having a correct decreasing order as plus 5, plus 3, minus 2. So, that's the answer. Question number 82. Among the 4 options given, which is not obtained by the aldol condensation between this compound and benzaldehyde? That is the question. That is not obtained. Not that it is not asked which is obtained. That is not obtained. So only one will, 3 will be obtained. 1 will not be obtained. We will see that. First, listen carefully. See, out of benzaldehyde does not have any alpha hydrogen, that is hydrogen on the next carbon to the carbonyl group. So, benzaldehyde alone cannot undergo aldol condensation only when alpha hydrogen, that is on the carbon adjacent to the carbonyl group, that must have at least 1 hydrogen, then only aldol condensation can take place. Isn't it? Aldol reaction can take place. Here, if you verify, this carbon does not have alpha hydrogen, but this carbon has 2 hydrogen. So, from this a carbanion can be formed for that which is required for aldol condensation. You have taken 2 different types of carbonyl compound. One is this ketone and the other is benzaldehyde. Benzaldehyde does not have alpha hydrogen. So, benzaldehyde cannot take part in the first step. Only this compound, this ketone alone can take part in the first step of forming a carbanion. What I mean, carbanion is formed from this compound only, not from benzaldehyde. This carbanion is formed. But, listen carefully. But once this carbanion is formed, it can attack either this carbonyl group or the carbonyl group of benzaldehyde. So, their chances are more. In the second stage, even benzaldehyde can take part. We will see the mechanism of the reaction. Listen carefully. See, if this carbanion attacks the carbonyl group of another molecule of the same type, see what happened, and see I haven't shown the whole steps. First it become O minus, then it comes back and become OH. See, it turns, if you remember the reaction, first it goes like this. If you want, I can write. Okay, listen. See, this one attacks the carbonyl group. For convenience, we write that in the inverted way, like this. The 2CS3 of this will be here. It will be first forming a carbon ion like that. It will capture a proton from the surrounding aqueous medium. Capture of a proton from an aqueous medium is shown by this way. Plus H2O minus OH minus mean 1H plus has been captured there. So what you get? This will be obtained. And what is the next step? Elimination of water molecule. How it eliminates water molecule? It can eliminate water molecule. Here also there is an alpha hydrogen. Here is also there is an alpha hydrogen to the OH group. OH. So it can form double bond here, isn't it? Or here. Not here because there is no hydrogen. So possibility we are writing. Listen carefully. A double bond okay. One possibility this. Plus the other one will not be formed because it is not stabilizing the molecule. Second possibility is theoretical only. In reality, it is not formed. How? Like this. What I presently draw actually will not be formed. Reason? It does not contribute to the stability. Okay. So, I have told you in this question, 3 are formed whereas 1 is not formed. That one which is not formed is this structure given as one of the option. That is our answer actually. Okay. Okay. So these are the 2 products possible. Then what are the other 2? Look here. It can attack the CHO group of the benzene ring, no? C double bond O H. It can attack this group. Okay. Then what immediately forms? This is the structure formed. See in the next step, here there is a hydrogen remaining. This H2O will be eliminated. Why? If that H2O is eliminated, it will be that double bond will be in conjugation with this CO group. Here also for the same reason, this double bond is formed. This double bond and this carbonyl group are in conjugation, so they can undergo resonance stabilization in between. Okay. The same reason here also a double bond is formed. While that double bond is formed, listen carefully. Double bond O, geometrical isomerism can happen. What do I mean? This double bond and benzene ring here, hydrogen here. Here there is also one hydrogen, you have to remember. One hydrogen is there. That is not eliminated. Or it can form the other geometrical isomer. A bit standard question. Oh, I cannot draw. I have to wipe it out and I draw. because space is not sufficient. We'll draw from the bottom. You have the aromatic ring there, like this. This and this are geometrical isomers. Both can be formed there. So which are the products formed? Formed products are this, and this. These three are formed. 1, 2 and 3. That is not formed is this. And why it is not formed? Because it produces a double bond which cannot conjugate with the carbonyl group, and so do not contribute or does not contribute to the stability of the product. That's why this alone is not formed. That is not formed. Okay, that is the answer. Among the 4 given options, this, whatever be its number, is the answer. Same explanation I have given here also in the note. Okay. So 1 is the answer. Structure 1 is that I have marked as red. Okay. So that leaves that. We proceed to the next question. Among the following compounds having conjugated double bond, only alternate number double bonds will have conjugation. 1, 3 heptadiene, that can conjugate. 1, 4 isolated double bond. 1, 5 isolated double bond. 1, 6 no doubt isolated double bond. Structure I have shown here. Only in 1, 3 double bonds are alternating. Double bond, single bond, double bond. Only then they can conjugate. Double bond, single bond, single bond, double bond. No. Double bond, single bond, single bond, single bond, double bond. No. Double bond, single bond, single bond, single bond, single bond, double bond. Not at all. So answer is 1. Simple question. Question number 84. Oxidation of para-nitrotoluene with acetic amino an acid that is stronger than benzoic acid. Statement 2. Reduction of para-nitrotoluene with a tin HCl followed by neutralization gives an amine that is more basic than aniline. What are these sentences meaning? First statement suggests acid KMNO4. If you oxidize this, it will give this acid, para-nitrobenzoic acid. Para-nitrobenzoic acid is stronger than benzoic acid because it is an electron withdrawing group through resonance, isn't it? So it is a correct statement. Carboxyl ion spreading negative. So it is a stronger than benzoic acid. That first statement is correct. Then about the basic strength. If you reduce this with the tin and HCl, it become this NO2 group become NH2. We know that. And this aniline is more basic than aniline itself. Why? Because this NH2 has a lone pair on it whose availability is made more due to the electron releasing nature of the methyl group, isn't it? So methyl group can release electron into the ring by 2 ways. Inductively it can release, but inductive effective will be very weak since it is in the para portion. But it can also hyperconjugate. We know that hyperconjugation is something like resonance. So more electron will come to amino group, making it more basic. So both statements are correct here. So both the given statements are correct. So option 1 is the answer. The green paramagnetic species formed by heating KMNO4. It is K2MnO4. Potassium manganate is a green crystal. We know reaction is this: 2 KMNO4 at 513 Kelvin giving K2MnO4 plus MnO2 plus O2. MnO2 is a dark powder. K2MnO4 is a green crystal. So the K2MnO4 is the answer. Okay, option 1 is the answer. Consider the following reaction and choose the correct option. We know chromyl chloride, carbon disulfide medium. second then hydrolyze, you get a benzaldehyde, isn't it? Benzaldehyde is the product, we concluded that. Then these statements are regarding the benzaldehyde. On treating compound P with that is benzaldehyde with the saturated NaCO3, brisk effervescence will be obtained. No, only carboxylic acids can produce brisk effervescence with the NaCO3, which is carbon dioxide. No, that is wrong. Compounds P can be prepared by treating benzene with the anhydrous aluminum chloride and acetyl chloride. No, that is acetophenone, not benzaldehyde. Acetophenone will be formed. Friedel-Crafts acetylation reaction, COCS3, that is. So this statement, it is not benzaldehyde, it is not P. So that's also wrong. Then, on treatment with the bromine water, compound P gives a white precipitate. No, there is no precipitation of anything with the bromine. No reaction. That's wrong. Compound P is obtained by hydrogenation of benzoyl chloride with the palladium on barium sulfate. That is correct. Benzoyl chloride, we know. Benzoyl chloride. Rosenmann's reduction, we are familiar with that. COCl, hydrogen, palladium, barium sulfate. You get benzaldehyde. You remember that. CHO. So that statement is correct. So option 4 is the correct answer. Benzoyl chloride with the palladium. That's correct. Yeah, benzaldehyde you get. Other explanation I have already given. An electrolyte 1:3 electrolyte means 1 cation, 3 anion. This gives 1 cation, 1 anion. This gives, here there's a, I have forgot to put that, 1 cation, 2 anion. 1 cation, 3 anion, that will be the answer. No ionization. So 3 is the answer. CONS3 6 times Cl3 will produce 1 cation and 3 anion. 87, 3 is the answer. 88. Consider the following schematic plot of orbital wave function psi r against distance r from the nucleus. The figure representing 2 radial node. 2 radial node means 2 nodal plane. Nodal planes are seen when the radius wave function meets 0 line. See, it has no nodal plane. It is not, see, it is tending to infinity. It is not touching the x-axis. It touches only at one spot. So it has only one radial node. Here the line is shifted over above. This is the line. And this line passes through that at 2 points. So it has 2 nodal plane. Here it is shown running parallel. It moves up to infinity. So it does not touch. There are no 3 points. Only 2 are there. Got that? Here also there is only 1. It moves to infinity before it touches. They touch. So only this case there are 2 radial node, means 2 empty spaces among various spheres of the same orbiter. That is called a nodal plane. Nodal space or radial node. Imagine 2 balls, one within the other. So in between these 2 balls there is a space, no? That is called a radial node. A spherical space, that is called radial node, where electron will never be present. That radial nodes they are talking about. And they are asking in which case there are 2 radial node. 2 radial node can happen when there is 3 regions of probability. One sphere, outside it another sphere, still outside it a third sphere. When there are 3 regions of probability, there will be 2 nodal space in between. When there are 4 regions of probability, there will be 3 nodal space. When there are 5 regions of probability, there will be 4 nodal space in between. Okay? So, this is our answer. And the last question. No, not last. Arrange the following molecules in the increasing order of polarity. We know carboxylic acid is having the highest polarity, followed by alcohol, then ketone, then ether. I repeat, carboxylic acid maximum, then among the given alcohol, then only ketone, then ether. Means D greater than B greater than C, D greater than B greater than C greater than A. 4 is the answer. 4. And the last question from molecular orbital theory. The highest occupied molecular orbital of neon, Ne2 has 20 electrons. This is the case. We see that all the orbitals are occupied by electron because we study only up to species having 20 electron. Ne2 is the last case. So its electronic configuration will have all the orbital we have learned in molecular orbital theory. Sigma 1s2, sigma 7s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px2, pi star 2pyz2, sigma star 2pz2. So here among the option sigma star 2p will be the answer. Answer will be 4. Agreed. Answer will be 4. Sigma star 2p. With that, we come to the end of the discussion of this ReNEET 2026. Okay, take care. Our next question, question number 49. In potash atom, the ratio of numbers of K plus and SO2 minus ions is 1:2, 2:1, 2:3, 3:2. It can be said to be from chemical bonding and molecular structure or chemical arithmetic, basic concepts of chemistry. Okay. And to get the answer, you must know the formula of the potash atom. It is K2SO4, Al2SO4 thrice 24H2O. And simply take the ratio of the number of potassium ions and number of sulfate ions, K2. So there are 2K plus. 2K plus is there. And how many sulfates are there? 1 sulfate in the K2SO4 part and 3 sulfate in the aluminum sulfate part, making a total of 4. So 2:4 means 1:2. So our answer for the question is 1. 1:2. The order is also important. It's not 2:1, 1:2. So our answer for this question is 1:2, which is answer 1. Okay. The next question. It is from biomolecule. The correct statement about peptides and proteins is. We will read each question and then itself we will decide whether it is correct or not instead of reading the whole question. Tertiary structure of proteins has 2 or more polypeptide subunits. Is that correct? It is not for the tertiary. It is not for primary, secondary or tertiary. It is for only for the quaternary structure we study about polypeptide subunits that act together as the quaternary structure. Okay, so that statement is incorrect. That is, only in quaternary structures you have polypeptides, separate units which act together. So, tertiary structure of protein has 2 or more polypeptide subunits is incorrect, an incorrect statement. Only proteins have a quaternary structure are biologically active. No. Of course, quaternary structures are biologically active, but in certain cases, only up to secondary structure is sufficient for some certain biological activity. In some other cases, only tertiary structures is sufficient for some biological activity. So, it can be either secondary, tertiary or quaternary structure for biological activity. So, that statement is also incorrect. Okay. In beta-pleated structures, peptide chains are held together by intermolecular hydrogen bonds. We have studied that. In beta-pleated structure, polypeptide chains lie adjacent and make CONH intermolecular bonding. Isn't it? Hydrogen bonding, intermolecular hydrogen bonding. So that statement is correct. In beta-pleated structure, it is intermolecular hydrogen bonding that keep the separate polypeptide chains that lie adjacent together. So that statement is correct. In alpha helix structure, the polypeptide chains is twisted into a left-handed screw helix through intramolecular hydrogen bonding. Of course, the second part, it is through intramolecular hydrogen bonding is correct, but it is not through a left-handed screw type, but through a right-handed helix. Right-handed helix, we have studied that. So that is also incorrect. So our answer for this particular question is question number 3, the question from biomolecule. Okay. Okay, the next question from basic concepts of chemistry. The first chapter, first year, or 11th standard. The numbers 17.0145 and 21.0235 were rounded off to 3 figures after decimal point. The resultant numbers respectively are, it is regarding rounding of the figures. Okay, rounding of the figures. You know that whenever the eliminated first figure is 5 or 5 followed by 0, then while you eliminate them, while you avoid them, you have to increase the last retained figure by 1 if it is odd, or simply discard the numbers to be eliminated if it is even. Here in this particular case, the first case, it is 17.0145. So while you discard 5, you don't have to increase the value of 4 because it is an even number. But while you discard 5 from 21.023, when 5 is eliminated, you have to increase 3 to 4 because it is an odd number. So 17.0145 becomes 17.014 and 21.0235 becomes 21.024. Means 3 is your answer for this simple question. Okay. The next question, question number 52, it is from equilibrium and it is related to solubility and solubility product. Okay. The correct question number 52, the correct order of solubilities of the given salts in water at 298 Kelvin. They have given 3 salts and their solubility products AgBr, ZnOH2 and Hg2Cl2. After solving, you have to find which is the correct order of solubility. Okay. See, for this, first we have to discuss AgBr. See, AgBr, how it ionizes? AgBr ionizes producing 1 cation and 1 anion, and Ag plus aqua S molar, like the solubility B S molar, and Br minus, since it is having 1 cation and 1 anion, the solution will have same concentration of Ag plus and Br minus. If we started with 1 mole AgBr, solubility, what is dissolved is the solubility. So aqueous S molar, aqueous S molar. Okay. KSP. What is KSP? KSP is the product of ionic concentration. Each concentration term having a power which is the coefficient in the formula. But here the coefficients of both Ag and Br is 1. So square bracket Ag plus into square bracket Br minus, isn't it? But we know that concentrations are here, so molarity itself. So it is S molar into S molar, isn't it? S molar into S molar. S molar into S is equal to S square. So what will be solubility? S is equal to square root of KSP. Since KSP is equal to S square, KSP is equal to S square, KSP is equal to S square, S will be square root of KSP. So what solubility is given in the question? Solubility values, solubility product is given in the question. It is 5.0 into 10 to the minus 13 for AgBr. So you take square root 5.0 into 10 to the minus 13. We have to remember, you are not provided with any calculator or a Clark's table, so you have to solve logically. We can first convert this 5.0 into 10 to the minus 13 into 50 into 10 to the minus 14, because powered values can be easily put to square root by dividing the numerator by 2. So we have to convert the odd power of 10 to an even power. For that we convert 10 to the minus 13 to 10 to the minus 14. To compensate, you multiply 5 with 10. So 5.0 into 10 to the minus 13 is equal to 50 into 10 to the minus 14 under root. So now a mild approximation. Square root of 49 is, we know, 7. So square root of 50 will be slightly more than that. So we approximate that the result is 7 into 10 to the minus 7 molar. Actually slightly more than this. Okay. So that we have concluded. Now we go to the next case. is an OH2. It is an AB2 type salt, so the calculation will be different. ZnOH2, if you started with 1 mole, Zn2 plus S molar and 2 OH minus, every cation produces 2 anions here, so the concentration, or in this particular case solubility, will be twice that of Zn2 plus. The anion's concentration will be double that of the cation. So here we have Zn2 plus S molar, but OH minus will be 2S molar. KSP we know, product of concentration, each concentration raised to a power, which is the coefficient. So it will be square bracket Zn2 plus into square bracket OH minus the square. What is a concentration of zinc? It is S. What is the concentration of OH minus? It is 2S, but it is also having the power 2 because coefficient is 2. So S into 2S square means 4S cube. So solubility S will be cube root of under root KSP by 4. From this equation we get a solubility S is equal to cube root of under root KSB by 4. In the question they have provided with the solubility product of ZnOH2 is 1 into 10 to the power of minus 15. So first we write cube root of under root 1 into 10 to the power minus 15 by 4. But 1 by 4 is 0.25 now. So now we have 0.25 into 10 to the power minus 15 under root. To make a value for which can be easily, whose cube root we can approximate, we make a modification. We convert 0.25 into 10 to the power minus 15 into 250 into 10 to the power minus 18. 18 is an even number. So we can find it's not only even number, it is divisible by 3. That you have to take care. It must be divisible by 3 because here we are going to divide it with 3, not with the 2, because it is cube root. Okay. So that's why we made it 10 to the power minus 18. Now the problem is to find the cube root of 250. It is only by trial and error method. We know 5 into 5 into 5, 125. Then 6 into 6 into 6, that we can easily calculate. It is 216. But our value is 250 now. Then we attempted 7 into 7 into 7, 343. So 250 is somewhat more closer to 216. So I approximated, or we have to approximate in the entrance sort 6 into 10 to the power minus 6 molar. It will be slightly more than, because instead of 250 we get 216 only. So we conclude that the real value will be slightly more than this, isn't it? Okay. Hope you understood that. So we got two values, not exact values. In problems we can do like that only. Okay. Third case, Hg2Cl2. Here you have to take a special care. See, you must be familiar with the Hg2Cl2. It does not ionize as 2Hg plus 2Cl minus. Mercurous remains as a single ion, Hd2 2 plus. So it is AB2 type, not A2B2 type. You must remember that, otherwise you will go wrong. So here the ionization is Hd2Cl2 2 plus, Hd2Cl2 reversibly giving Hd2 2 plus S molar plus 2Cl minus, that will be double the concentration of Hd2 2 plus 2S molar. Then so KSP is equal to Hd2 square bracket Hd2 2 plus into square bracket Cl minus the square. Again it is of the type S into 2S square, as in the previous case, 4S cube. So S is equal to, as in the previous case, cube root of KSB by 4. Here it is cube root of 1.3 into 10 to the power minus 18. The value is given in the question. So I first divided 1.3 by 4. So I got 0.325 into 10 to the power minus 18. Okay. It is approximated to, it is converted to 325 into 10 to the power minus 21. Okay. So that I can approximate the cube root of 325. Okay. Here we have to find out the cube root of 325 as an approximation method. As in the previous problem, 6 into 6 into 6, 216. And 7 into 7 into 7 we can calculate 343. This value is lesser than 343. So I approximated here. It is 7 into 10 to the power minus 7 molar again. Even in the previous case it was 7 into 10 to the power minus 7 molar. Okay. But here it will be slightly less than this. Because when it is 343, it is 7. But here it is only 325 no. So it will be slightly less than 7 into 10 to the minus 7. Only when it is 343, it would be exactly 7 into 10 to the minus 7. Since it is 325, it will be slightly less than. So now the three values we have, I have missed to write 6 here. 6 into 10 to the minus 6. 7 into 10 to the minus 7 slightly more than this. 7 into 10 to the minus 7 slightly less than this. So solubilities will be of the order. From this discussion, zinc hydroxide is the most soluble, followed by AgBr and least for Hg2Cl2. Okay, so our correct answer among the given list, I am not going back, it is fourth one. ZnOH2 is greater than AgBr and still greater than Hg2Cl. Hg2Cl2 is the least soluble salt here. So please remember, such problems do not give you exact answers. You have to make logical, wise conclusions, simplification, approximation. Okay, take care. The next question is 66. This can be said to be from coordination compounds. It is regarding the magnetism shown by different complexes, which in turn depends upon the number of unpaired electron in that complex molecule. Okay. Among the species given below, the spin-only magnetic moment is highest for given atomic numbers of titanium, manganese, iron and cobalt are respectively 22, 25, 26 and 27. Four complexes are given. We have to find out the magnetic moment or number of unpaired electron in each case. Greater the number of unpaired electron, greater will be the magnetic moment. Okay. First case, manganese MnCN6 minus. For that, they have provided the atomic number of manganese. See, remember, in neutral manganese atom, which has 25 electron, the valence electronic configuration, if you remember, is 4s1. It is wrongly shown as 4s. I'm sorry, it is 4s2 here, not 4s1. It is wrongly typed as 4s1. 4s2 3d5. 4s2 3d5. Okay, now in the complex formed MnCN6 minus, the oxidation state of manganese is plus 3. Then only after 6 minus charge being attached to it, the remaining resultant charge is 3 minus. So it must be Mn3 plus. So 3 electrons must be lost from here. Valence electronic configuration of Mn3 plus. See, we know by the rule, one or both s electrons are removed prior to the removal of any d electron. So these two are removed, along with that one from this also removed. So this 2 and this is removed. So in the Mn3 plus ion, the valence configuration is 4s0 3d4. 1, 2, 3, 4. Next, we have to think about the nature of the ligand. We know cyanide is one of the strongest ligand. It have the capacity to pair up the unpaired electron to generate vacancies in the inner d orbital, because inner d orbital involving complex are more stable. So it will try to do that. Since there are 4 unpaired electron, 4 unpaired electron means 1 vacant orbital is already there. For the hybridization d2sp3, it will require 1 more vacant d orbital only. So one of the electron get paired up, generating 2 vacancies here. Okay. So after generating 2 vacancies, it forms d2sp3 hybridization, resulting in the formation of 6 d2sp3. 6 hybridized d2sp3 orbitals, in which the ligand cyanide will form coordinate bonds. Okay, so our concern is regarding the number of unpaired electrons here. There are only 2 unpaired electrons here. We know the spin-only magnetic moment is given by the formula root of n into n plus 2, where n is the number of unpaired electrons. It is 2 here. So we don't have to calculate n into n plus 2 to decide which is the strongest magnet. Okay, which is the strongest magnetism. So for the time being, we stop here. 2 unpaired electrons are there. So we proceed to the next case, FeCN6 minus. Next case. First we have to start from the iron atom. iron atom with the atomic number 26, one electron more than that of manganese. So you have to pair up one more electron in the D. So its valence electronic configuration is like this, 4s2 3d6. Okay. Now in the complex, as in the previous case, iron will be in the +3 state. Then only 3 minus charge will remain. Okay, +3 state. Agreed. Okay, so 3 electron must go. Okay. So what happened? The pair of s electron and one of the pair from the pair one more electron will be removed, so that 3d5 4s0 3d5 will be Fe3 plus configuration with the 5 unpaired electron. But we know cyanide is again a strong ligand. For the time being, there are no vacant or d orbital at all. So it requires 2 vacant d orbital, isn't it, to undergo D2sp3 hybridization. It will transfer 2 electrons into this, producing an electronic configuration like this. 1 orbital, 2nd orbital, 3rd orbital. So 4th and 5th orbitals are vacant. So it can now undergo D2sp3 hybridization. So what is our concern? There is only 1 unpaired electron here. Previous case there were 2 unpaired electron. Here only 1 unpaired electron. So its magnetism will be less than the previous case. Now we proceed to the 3rd case. Ammonium is a moderately strong ligand, and here CONS3 is 6 times 3 plus. Since cobalt has a 3 plus charge, due to the strong positive charge of the central nucleus, central cobalt ion, ammonia will act as a strong ligand here. Keep that in mind. Okay. So since ammonia molecules are neutral ligands, the whole 3 plus charges are due to cobalt 3 plus. Cobalt only. So cobalt's oxidation state is +3. We know that. Okay. So to start with the cobalt atomic number 27. So in neutral cobalt atom, one more than the iron. So one more will be paired up. 4s is already paired. 3d, 2 pairs will be there. 3 unpaired electron will be there. Again, it must get converted to CO3 plus, for which 3 electron must be removed. These 2 will be removed, and 1 from here also will be removed. So 4 unpaired electron will result like this. 4 unpaired electron will result like this. For the time being, there are no vacant orbital, but ammonia, since acting as a strong ligand here, will force the electron to pair up to generate vacancies, create vacancies. Then these 2 will get promoted over here, so that the new configuration will change to this. There are 2 vacant orbitals. Okay. Here, there are no unpaired electron at all. So it will have 0 magnetic moment. Agreed. In the first case, it was 1, then 2, then here it is only 0. Okay. And the last case, we are proceeding to Ti. Titanium, scandium titanium, the second D block metal it is, isn't it? So its configuration 4s2 with the 2 more occupied. Here, since all the 3 vacant orbitals are already there, 3 vacant orbitals are already there, it does not have to undergo any hybridization at all. I'm sorry, it does not have to undergo any electron change position pairing up at all. So this will also have 2 electron in the d orbital. No, I made a mistake. I'm sorry. This is the vacant electronic configuration of titanium only. We want in TiS2O3 plus, S2O6 3 plus, there are 3 electron to be removed, and so this pair as well as 1 more will be removed. So its electronic configuration 4s0 3d1, isn't it? 4s0 3d1. Here I have to say that the other thing, that is, it does not require any pairing up because 4 vacant orbitals are there. So it can directly undergo hybridization. Okay. D2sp3 hybridization. So it will have 1 unpaired electron. You got that? 1 unpaired electron. So out of the 4 cases we have discussed, which is having maximum number of unpaired electron, without going back, which one? We have to go back. I forgot. Yeah, the first case, isn't it? The first case will have 2 unpaired electrons. So answer the very first one. Okay, 2 unpaired electron, 1 unpaired electron, 0 unpaired electron, 1 unpaired electron. This were the order in which we found the number of unpaired electron in the respective cases. So here in this particular case of 1 manganese hexacyano manganate, okay, hexacyano manganate 3, there are 2 unpaired electron in the complex ion, making that the species with the highest magnetic moment. Okay. We proceed to the next question. The next is from lanthanides and actinides of the D and F block elements. Okay. The lanthanide ion having the 4 unpaired electron. This question warns you that you have to make by heart the electronic configuration. Not only that, lanthanides and actinides in the respective order you have to make by heart. Not only that, the order in which electrons get removed from them, then only you can decide what will be the present electronic configuration of various ions formed from lanthanides and actinides. So there are a lot of things to be remembered. Here they have provided 4 lanthanide ions, and you have to decide which has the correct electronic configuration. Okay. The lanthanides having 4 unpaired electrons is, that's the question. So we start for cerium. Cerium 4 of 1, 5d1, 6s2. Cerium 3 plus S and D will be removed first. This will become 0, this will become 0. 4 of 1 only. So 1 unpaired electron. Then neodymium, Nd. 4 of 4, 5d0, 6s2. First 2 S electron will be removed, then 2 from here will be removed. Isn't it? It is neodymium 3 plus. So 2 will be removed from here, 1 will be removed from here. So neodymium 3 plus has the configuration 4 of 3, 5d0, 6s2. Only 3 unpaired electron will remain. And now the terbium 4 of 9, 5d0, 6s2. Tb3 4 of 8, 5d0, 6s0. 2 removed from here. And from the 9, 1 is removed, so that it becomes 4 of 8. Okay, 1 parent. So what happened? 4 of 8, we know 7 orbitals are there. When it is 8, 1 will get paired. The remaining 6 will be unpaired electron. We are not concerned, we are not talking about that having the maximum number of unpaired electron, but that is having 4 of unpaired electron. Okay, so that cannot be the case because it is having more than 4 electrons. In the last case, holmium 4 of 11, 5d0, 6s0. After removing 3 electron, this 2 gone, and this become 10. 4 of 10. 4 of 10. 7 orbitals. 3 pairs and 4 unpaired. 3 pair means 6. 4 unpaired. 6 plus 4, 10. So when there are 10 electrons in the F subshell, it will be having 3 pairs and 4 unpaired electrons. So that will be our answer for this question. 4th is the answer. Okay. You have to speed up because 45 questions you have to cover. No? Next is rather easier one. The formula of tetramine aqua chlorido 3 chloride. Tetramine means 4 ammonia molecule must be there. Aqua, 1 water molecule must be there. Chlorido, 1 chlorine must be within the complex ion. Tetramine aqua chlorido. And what about the chloride? It is 3. Cobalt is 3 having 3 positive charge must be, so there must be as a whole 3 chloride ion, not 2 or 1. So look, cobalt, tetramine, aqua, chlorido, not only that, total chloride 3. So cobalt's charge is plus 3. So for this question, 68 answer will be 4. Got that, no? Okay, 4. Okay. And the next question, question number 69. See, this question actually belongs to physics. It is based on Carnot cycle. Even though we study thermodynamics in chemistry, it is mostly of thermochemical nature. Actually, we are learning thermochemistry, and this kind of information comes only from physics. Somehow they have included that question here, probably because a student who is preparing for NEET have to definitely prepare for physics along with the chemistry. Maybe that's the reason. Okay, what is this Carnot cycle? It's a cyclic reversible process comprising of isothermal expansion, adiabatic expansion, isothermal compression followed by adiabatic compression. Okay. See, my face is not available because of this white background here. Okay. See, the first thing to happen, a definite amount of gas is reversibly expanding from state A to state B from P1 V1 to P2 V2 isothermally at constant temperature of T1 by absorbing a quantity of heat Q1. The corresponding work W1 is equal to heat is absorbed from the surrounding Q1, and work done by a system as per the physics rule is positive. In chemistry we study it as negative. Here they have even applied the conventions of physics. That's why I said it should not have been asked in chemistry question paper, because we are more in chemistry we are prone to put work done by a system as negative. See, here it is physics, so it is positive. nR T1 log V2 by final volume by initial volume. Okay, the green part we will see later. Then W2, it is adiabatic expansion from P2 V2 to P3 V3. See, during adiabatic process heat is neither absorbed or released, so work is done at the expense of the internal energy, and here, due to this adiabatic expansion, the temperature, since the work is done by the system, its temperature drops, okay, from T1 to T2. So, from P2 V2 to P3 V3, it is adiabatic expansion, and temperature changes from, that is not indicated in the diagram, T1 to T2 here, okay. Then it reaches point C. From there, it again undergo isothermal reversible compression so that volume decreases, pressure increases along this. Here the temperature, the T2 attained here is retained throughout the isothermal expansion, isothermal contraction process at T2, and during isothermal contraction, heat will be released because the heat content due to compression heat is generated, which is released because it has to happen isothermally, that is at constant temperature. So heat must be slowly released into the surrounding. Okay, isothermal reversible compression. Okay, happening at the temperature T2 when Q2 heat is released. One more point I forgot to tell. The work of adiabatic expansion is given by the formula nR final temperature minus initial temperature divided by gamma minus compressibility factor gamma minus 1. Okay, ratio of Cp and Cv is gamma, so gamma minus 1. Okay, green part we will say later. Now, again, third case, isothermal reversible expansion, as I have mentioned here. W3 is Q2. Here, work is done on the system because it is compression. When work is done on the system, the sign of, so by the physics sign convention, it is negative nR T2 log V4 by V3. Okay. Final volume V4, initial volume V3. It is P4 V4 after isothermal compression D. A, B, C, D, P4 V4. Okay. And finally, it undergoes the adiabatic compression from P4 V4 to the initial, not P5 V5, the initial P1 V1 back. Okay. So it is a cyclic reversible process. The net process is cyclic and reversible. P4 V4. Here we know that temperature, since it reaches back P1 V1, temperature also reaches back T1. So during this process, temperature changes from T2 to T1, but Q2 no heat change happens because it is adiabatic. And the corresponding equation similar to W2, the corresponding equation for W4 is NR final temperature T1 minus initial temperature T2, not T2 by T2 minus T1, T1 minus T2 divided by gamma minus 1. Okay. Oh, okay. Oh, you can rearrange it as minus NR T2 minus T1 gamma minus 1. Okay. Okay. Now, what are the questions options given? In the option they have given 4 equations. W1, W2. W1 by W1 plus W2. Look here. W1, W3, not W2. W1 by W3 is equal to 2 T1 ln V2 by V1 minus 2 T2 ln V4 by V3. Is that correct? We will check. W1 plus W3. This is why I have put the green writing for our particular answer. See, it was in the question it is mentioned R is 2, N is 1. 1 mole gas is considered and R is taken as 2 calorie. So 1 into 2, 2. So this equation produces to 2 T1 ln V2 by V1. And similarly this equation R is 2, N is 1 minus T2 ln V4 by V3. And the first option given, as I told you, what is that? W 2 T1 ln V2 by V1 minus 2 T2 ln V4 by V3. Yeah, it is correct. Adding these two, 2 T1 ln V2 by V1 minus adding this, so in effect negative, minus T2 ln V4 by V3. So the first statement is correct. That immediately follows. What immediately follows? The next 3 must be wrong. Next one, W2 plus W4 is delta U2 plus delta U2 minus delta U4. They are talking about delta W2 and W4. W2 and W4. Look here. W2 and W4. See, here the work involved is nothing but the change in internal energy, because no energy is permitted to be given out or taken in because it is under adiabatic condition. So the W2 is nothing but delta U2 here, and the W4, another adiabatic process, is equal to delta U4. So W2 plus W4 must be delta U2 plus delta U4. Its sign may later on changes to negative upon substitution, not before that. Got that? It's a value when substituted can be negative, but not the original equation. So W2 plus W4 must be delta U2 plus delta U4 and not delta U2 minus delta U4. For that reason, the given option WU2 minus WU4 U2 minus delta U4 is wrong. This one, delta U2 plus delta U4 is the correct answer. So that is wrong. And what is the third option? Look here. W1 plus W2, that is first isothermal and first adiabatic sum 2 T1 ln V1 V2 by V1. Is that correct? W1 by W2? No, it cannot be. W1 plus W2, one is a term involving logarithm, other does not involve logarithm. It's sum. That cannot be the given result, isn't it? The given option. That cannot be the given option, which is 2 T1 ln V2 by V1. 2 T1 ln, this alone is given as the answer, which is incorrect. Okay. This sum of W1 and W2 cannot be this alone. So that is wrong. Last one, W1 plus W2 plus W3 plus W4 is equal to 0. The net work involved is 0. No, since it also involved isothermal and adiabatic processes, the net work involved is the area covered by these 4 curves. So the last option is also incorrect. So we conclude that in this particular case, 1 is the answer. Okay. Okay, next question. Given below 2 statements, one is labeled as assertion and the other is labeled as reason. Assertion. The first ionization enthalpy of oxygen is lower than those of nitrogen and fluorine. First ionization enthalpy of oxygen is lower than those of nitrogen and fluorine. Reason. The loss of an electron from oxygen leads to stable half-filled P. Actually, it should have been subshell. They have wrongly given it as orbital. Okay. Reason, the loss of an electron from O leads to the stable half-filled p subshell. Okay. Let's see. See, oxygen, nitrogen, oxygen, fluorine. These are the three elements. See, what is the valence EC of nitrogen? 2s2, 2p3. Oxygen, 2s2, 2p4. Fluorine, neighboring elements. Fluorine, 2s2, 2p5. Isn't it? What the assertion says, removing this electron requires less energy than removing one electron from here and removing one electron from here. Means the first ionization energy for oxygen is less than both this and this. Can you explain? Yeah, there are actually the reasons are different. Here, the stable electronic configuration gives it a higher ionization energy, nitrogen. For nitrogen, ionization energy should be actually increasing from nitrogen to oxygen to fluorine because atomic size is decreasing. But unexpectedly, nitrogen has a higher ionization energy than its next member oxygen just because of the stable electronic configuration. So we conclude that oxygen has a higher ionization energy than nitrogen. Lower ionization energy than nitrogen. Actually, nitrogen is acquiring a higher ionization energy due to its half-filled state that brings oxygen's first ionization energy lesser. Comparing with the fluorine, or comparing oxygen with the fluorine, it is having more ionization energy because it is having a stable, nucleus with a greater charge. So here, fluorine is having high ionization energy than oxygen because its nucleus, its atom is small. Not only that, its nucleus is having one proton greater than that of oxygen. So, oxygen's ionization energy is less than this due to one reason and also due to this due to another reason. And so the assertion is correct. What about the reason? The reason says that by losing one electron, it acquires nitrogen's stable electronic configuration. Okay, it hasn't mentioned about this. It mentions that that reason is actually partially correct. But the given answer is assertion is correct, reason is correct. You got that? Reason given is that by removing this electron, oxygen acquires the stable configuration of nitrogen, half-filled state. That is correct. But there should also have been mentioning that it is having lesser ionization, its a nuclear charge is less than that of fluorine, but they haven't mentioned yet. They have accepted that as the reason. Okay. So, look here. Reason, the loss of an electron from oxygen leads to stable half-filled p subshell as that of nitrogen. Okay, that is correct. So, here the answer is both assertion and reason are correct and the reason justifies the assertion. Okay, hope you understood that. We proceed to the next. Consider the following statement about the solutions mixed by two liquids. An ideal solution thus formed obeys Raoult's law throughout the composition range. That is correct. Yes, a mixture of two liquids can be said to be an ideal solution provided if they obey Raoult's law throughout the range of mixing. Okay. Mixture of chloroform and acetone shows negative deviation from Raoult's law. Yeah, correct. Chloroform and acetone. CHCl3. CHCl3 and acetone, O double bond C, CH3. You know that in between these two, hydrogen bonds can be formed. Okay, so due to enhanced intermolecular attraction, it shows negative deviation. But you may have a doubt. This hydrogen is attached to carbon only, not to nitrogen, oxygen or fluorine. Then how can it form hydrogen bond? The reason is simple that due to the strong electron withdrawing nature of these three chlorine, the hydrogen on carbon as a special case acquire the ability to form hydrogen bond here. That's why it is forming hydrogen bond. And so that statement is correct. Mixture of chloroform and acetone shows negative deviation from Raoult's law. Next, mixture of aniline and phenol shows positive deviation. That must be incorrect. Phenol. And aniline, NH2. There is every chance that hydrogen bonds are formed. Okay, or like this. Hydrogen bonds are there. So that this pair also would show negative deviation. So only statement A and B are correct. Option 1 is the answer. An ideal solution thus formed this is not recorded there. An ideal solution formed obeys Raoult's law throughout the composition range is correct. Mixture of chloroform and acetone show negative deviation correct. Mixture of aniline and phenol shows positive deviation is wrong because it also shows negative deviation. So option 1 is the correct answer. Next, one of the product formed in the following reaction. This is cyclohexyl magnesium bromide. This is cyclohexyl amine. What will be the product? We know that whenever Grignard reagent is treated with a compound containing active hydrogen, a replaceable hydrogen. What are compounds containing active hydrogen? Water is an active compound containing active hydrogen. Amines, primary, secondary amines are compound containing active hydrogen. Carboxylic acids are a compound containing active hydrogen. Phenol is in a compound containing active hydrogen. All these can, but alkyl hydrogens are not active. So here what really happens is that this hydrogen replaces this MgBr, forming this cyclohexane. Okay, and the MgBr goes along with this NH. So our answer for this question will be 4, and the reaction is like this: MgBr plus NH2, cyclohexane plus cyclohexyl amine with MgBr attached to it. Hope you understood that. Okay. The next question. The correct statement. Boron has a maximum covalency of 4. Boron 1s2, 2s2. So its valence electron is in the second shell. Agreed. 2s2 also have 3 more orbital 2p. So making use of all these 4 orbital, it can form a maximum tetracovalency, as in BeCl4 2 minus ion. Okay, so boron can have a maximum covalency of 4. Beryllium, boron, I made a mistake. Boron is, you have to remember, boron is also an element coming to the second period. It is correct. Even by wiping out that E, BCl4 2 minus is correct. BCl6 3 minus is not shown. BCl4, boron tetrachloride with the 1 minus charge. BCl4 minus charge. Beryllium has 3 valence orbital. Beryllium as well as boron. Remember, beryllium as well as boron both belong to the second period elements, isn't it? Both of them are having 2s and 2p orbitals only. Beryllium as well as boron. Beryllium 1s2, 2s2. Boron 1s2, 2s2, 2p1. So both are having 1 2s orbital and 3 2p orbital. Correct, valid for both. It is similarly form what? BeCl4, which I have written earlier. This is BCl4 single minus, this is BeCl4 2 minus. Okay, beryllium has 3 valence orbital is wrong because this is correct. Boron has a maximum valence of 4 is correct. This is wrong. It has 4 orbital. So beryllium has 3 valence orbital is wrong. Both the boron and beryllium are having 3 or 4 orbitals. Magnesium has a maximum covalency of 4 wrong because magnesium can form hexavalent ions like this. Hexahydrate ions like this, Mg, because it belongs to the third period. it can make use of 3s, 3p and 3d orbital. So it can show up to a coordination number of 6. So maximum valency of 4 is wrong. Aluminium has 5 valence orbital. Magnesium and aluminium both belongs to third period. So 3s, 3p, 3d. 9 orbital it is valence. Aluminium has a 3s orbital is there, 3p orbital is there, 3d orbitals are there. So that is also wrong. It has have more than 5 orbitals. So here the only correct statement is which one? Boron has a maximum valence of 4. Okay? Yes. Yes. The next question, question number 58. According to crystal field theory, the correct ligands, the correct order of the ligands with respect to their decreasing order of field strength is. See, this is a direct question from coordination chemistry where you have to learn a systematic order of ligating power of various ligands. And you have to make that by heart. Okay. And if you remember, the first member in that series is carbonyl group, CO, carbon monoxide molecule, which is named carbonyl in the complex chemistry. Second coming is ammonia, if you remember, followed by H2O and least by Cl minus. So here the very first answer, number 1, CO greater than NH3 greater than H2O greater than Cl minus is the correct answer. Okay. The next question. 2 moles of an ideal gas undergo free expansion from 10 liter to 100 liter at 300 Kelvin. The values of delta S system and delta S surrounding are. R is the universal gas constant. This question is definitely from thermodynamics, and if you remember, the equation for delta S system is 2.3 nr log V2 by V1. Okay, so here 2 moles are taken, so 2.3 into 2 R log 100 by 10. 2.3 into 2 R log is equal to 4.606 R. And what about that's about the delta S system. What about delta S surroundings? Since it is a free expansion, it involves no work, no heat exchange is happening. So delta S surrounding will be 0. Delta S surrounding will be 0. So among the option, which one is the correct answer? Answer 4. Delta S system 4.606 R, and delta S surrounding, I have forgot to type R here. The correct answer 4.606 R, and delta S surrounding 0 is the right answer. Okay. The next question. It is from question number 60. It is from chemical kinetics. 2A giving B, rate constant being shown as small k, is a zero-order reaction where k is 1 mole per liter per minute. Rate constant is 1 mole per liter per minute. If the initial concentration of A is 2 molar, then time taken to complete 75% of the reaction will be. Okay, chemical kinetics. See, we know if the reaction were A giving B, the rate equation is minus dA by dt is equal to plus dB by dt is equal to K, because here the rate is independent of the concentration and is a rate itself is the rate constant. But the difference here is it is two-way giving products. Two-way giving products, that difference will be reflected in our approach. See, we know K is 1 by 2 dA by dt is equal to K. K we also know to be A0 minus AT by T for A giving B type reaction. Listen, rate constant K is equal to square bracket A initial minus square bracket A final divided by T. But here it is 2A giving products, so we have to multiply this with the 1 inverse of that coefficient 1 by 2. So K will be 1 by 2 into A0 minus AT by T, or T is equal to 1 by 2 into A0 minus AT by K. Now we substitute 1 by 2, initial concentration 2 molar. What is the final concentration? See, after as per the question, the remaining concentration will be 25% of the initial concentration because they are asking the time for the completion of 75% of the reaction. So since you have started from 2 molar, the remaining concentration will be 25% of the initial concentration, 2 into 25%. So 2 minus 80 or the remaining concentration 2 into 25% divided by K has been given to be 1 in the question. Then upon simplification, you get a 0.75 minute as the answer for this question. The specialty of this question or the thing you have to take care of is that you have to multiply with 1 by 2. Okay? Since it is two-way giving product. Question number 61. Given below are two statements. One is labeled as assertion and the other assertion reason type. What is the assertion? Generally, 3D transition metals have high melting points. Reason: involvement of 3D electrons in addition to 4s electrons in the interatomic metallic bonding. See here, it is from DNF block element doubtless, and it is very clear that the reason, assertion as well as reason are correct. Not only that, the reason explains why the assertion statement is valid. See, we know that generally D block metals have high melting point. Of course, exceptions are there due to specific reasons like mercury. Okay, so generally D block metals have high melting point than S block elements, S block metals. Why? Because here the additional penultimate d electrons are also involved in the interatomic binding of atoms together. Got that? So there are more electrons to bind the atoms together in the D block metals. That's why they have generally high melting point. So in the very explanation I have provided, I have mentioned not only the assertion but also the reason too. Generally 3D transition metals have high melting point. Reason: involvement of 3D electrons in addition to 4s electrons in the atomic metallic bonding. So here both assertion as well as reason are correct. Not only that, reason justifies the assertion too. So option is 1 for this question. Okay, the next one. For a salt XY, which is a strong electrolyte, the plot of lambda molar versus under root square root of concentration has a slope of minus 90.0 centimeter square mole to the power of minus 3 by 2 liter to the power of 1 by 2 at a 298 Kelvin. At a 0.01 molar concentration of XY, the value of lambda molar is 145.0 Siemens centimeter square mole to the power of minus 1. The limiting molar conductivity of Y minus. You are provided lambda, that is, you have to find out lambda 0 Y minus, lambda standard Y minus in Siemens centimeter square mole to the power of minus 1 at a 298 Kelvin. You are given lambda 0 X plus is given. This question may be felt confusing only if you are not familiar with the equation, Kohlrausch's equation, that for a strong electrolyte, a plot of lambda m versus root c is a straight line. Okay, straight line. And for that we have a straight line equation as lambda molar is equal to minus b into root c plus lambda infinite or lambda at the infinite dilution, isn't it? So see, most of the things we require to solve this problem is directly given. It is not at all an indirect problem. See, for instance, in this particular problem, lambda molar at the given concentration is given to be 145. Slope of the straight line is also directly given, minus 90. Concentration is given as 0.01. So, minus b into root c, root of 0.01. Then, at the infinite dilution, we know that the total conductance is the sum of ionic conductance of cation and anion. Among them, conductance of cation is given. So, what is the only unknown? It is the conductance of the anion at infinite dilution. So, you simply substitute it. 145 is equal to minus 90 into 0.01 plus root, within bracket 74 plus lambda 0 y minus. Here 1 by 0.01 can be resubstituted as 1 by 100. 1 by 100 is root of 1 by 100 is 1 by 10, and so upon simplification you can easily simplify without the need of a calculator etc. For that simplification you get lambda 0 y minus to be 80 Siemens centimeter square more to the power of minus 1. That is the first answer in the given among the given options. Okay. Question number 63. The amount of carbon dioxide evolved upon complete combustion of 116. I'm sorry. The amount of carbon dioxide evolved upon the complete combustion of 116 gram of N-butane. Given atomic masses. Okay. See, what is the molar mass of butane's formula? C4H10. So what is its molecular mass or molar mass? C4. 4 12 of 48 plus 10 58. Okay. Out of 58, you know there are 4 moles of carbon. See, out of 58, since there are 4 moles of carbon, that would lead to the production of 4 moles of CO2. Agreed. So, if you burn 58 gram, listen carefully, if you burn 1 mole of butane, which contain 4 mole of carbon, 4 mole of carbon dioxide will be produced, means 4 into 44 grams of carbon dioxide will be produced. So, listen, from 58 gram, how much carbon dioxide you get? 4 into 44, 176 gram. From 58 gram, 176 gram carbon dioxide will be generated. Very simple. Okay. In that case, for 116 gram butane, in that case for 160 gram butane, how much carbon dioxide will be evolved? It is 176 by 58 into 116, which is 352 gram. Again, it is the first option among the given. Simple question from basic concepts of chemistry. Okay. Next one. For an elementary chemical reaction, the Arrhenius plot is given below. In that plot, it is Arrhenius plot, ln k versus 1 by t. We are familiar with it. It is a straight line, we know. And here it is given ln k's initial termination point on y-axis is 6. It is given. ln k versus 1 by t is plotted. And where the line meets y-axis, ln k's value is 6. Remember that. What is the question? If the energy of activation is 6.64 kilojoule per mole and R is 8.33 joule per Kelvin per mole, the temperature at which the rate constant becomes E square per minute is. That's the question. Don't get confused by seeing E square per minute, etc. It is not that much troublesome. It is very easy rather. See, what is Arrhenius equation? Its exponential form. K is equal to A into e to the power of minus A by RT. K is equal to A, Arrhenius parameter A into e to the power of minus A by RT. Isn't it? Or it's a natural logarithmic form, how it comes. Ln K is equal to ln A minus A by RT. But here they have provided that E square is the, suppose the K value is E square. Now substitute that. Ln E square. But ln E square is 2L by the rule of logarithm 2 ln E. And we know that log 10 is 1. Similarly, natural logarithm of E is also 1 because log based to 10, and when log is based to the 10, then if you take log 10 it is 1. When log is based to E, then ln E will also be 1 for the same reason. Okay, 2 ln E is equal to 2 is equal to complete the equation ln A minus EA by RT. Agreed. Ln E square is equal to 2 ln E is equal to 2 is equal to ln A minus EA by RT. From the given diagram, see the highest value of ln K is ln A. That you have to remember. The higher, what is rate constant actually? It is the high, what is Arrhenius parameter A is actually, it is the highest possible value of rate constant. It is the highest possible value of the rate constant when temperature tends to infinity. In the plot, look back to the plot. See, when t becomes infinity, 1 by t tends to 0. So you go back in the x-axis and meet the origin. At that point, ln k takes a constant value because the line intersects with the y-axis, where ln k takes the highest possible value, means ln k becomes ln A. Okay, highest possible value of rate constant is called Arrhenius parameter A. So when temperature tends to infinity, 1 by t tends to 0. So value of ln k corresponding to infinite temperature, which is 1 by t, is ln A. So ln A is nothing but ln k, which is 6 here as per the diagram given. Okay. So 6 minus ln A 6, 2 is equal to, we will go again. See, ln E square is equal to 2, ln E is equal to 2 is equal to ln A minus EA by RT. Therefore, 2 is equal to 6 minus EA by RT. EA value you have to substitute in joule, and R is also in joule, not kilojoule. Then you find out T from the equation. You can do it very easily, and you get that equal to 199.2, very near to 200 Kelvin. Some calculation is involved there. It's not direct simplification. After doing that, you will get to 199.2, which is taken to be 200 Kelvin among the options given. Okay, so here the option 3 will be the right answer. It is from kinetics. And the 65th question. Given below are two statements. Statement 1. Heating NaCl with the concentrated H2SO4 and MnO2 results in the oxidation of Mn. Stating next statement 2. It is statement type, not assertion reason type. Heating NaI with the concentrated H2SO4 and MnO2 results in the reduction of Mn. In one case, MnO2 oxidation of Mn, and in the other case, reduction of Mn. Are they correct? We will check. For that, we have to be familiar with the chemical equations of them. Okay, these reactions are studied in D block elements. 4 NaCl plus MnO2 plus 4 H2SO4. If you heat sodium chloride and manganese dioxide with sulfuric acid, chlorine gas will be evolved. Okay. Similarly, if you heat manganese dioxide with the sulfuric acid and sodium iodide, violet vapors of iodine will be evolved. Okay, that's a method to generate chlorine gas as well as iodine gas. Look here, 4 NaCl, you have to make them by heart. 4 NaCl plus MnO2 plus 4 H2SO4 giving 4 NaHSO4 plus MnCl2 plus 2 H2O plus Cl2. So what happened to the oxidation state of manganese? See, in MnO2, Mn is in plus 4 oxidation state. Okay. And in MnCl2, it will get reduced to 2 plus, no? 2 plus, Mn2 plus. So Mn4 is reduced to Mn2. So the first statement is incorrect because it is not oxidation, it is reduction only. Okay. What about the next one? Here also 2Na plus MnO2 give plus 3. There is a slight difference in this reaction. There is no, here even the MnCl2 is formed, here MnI2 is not formed. That's the main difference. 2NaHSO4 plus MnSO4 plus 2H2O plus I2. That is, here also similar change take place. Mn4 is reduced to Mn2 here, but it is given as a reduction, so that statement is correct. So the first statement is wrong because here in both cases a reduction is happening to MnO2. But in the given statement, first case was mentioned as oxidation and second case was mentioned as reduction. That is wrong. Both are reduction. So statement 1 is incorrect and statement 2 is correct. Okay. So for this question, option 4 among the given, if you check, you will see that option 4 is the right answer. Okay. Okay. Then we proceed to the 74th question. A protein undergoes reversible thermal denaturation from its initial state N to denatured state D according to N reversibly giving D. At 60 degrees Celsius, the concentration of both N and D are equal at equilibrium, and the standard enthalpy of denaturation is 666 kJ per mole. The standard entropy change delta is 0 in kilojoule per Kelvin per mole of the protein upon denaturation at 60 degrees Celsius is closest to. Okay, we want to find entropy. You are given with the enthalpy. You are given an idea regarding equilibrium constant. Enthalpy, entropy, equilibrium constant. How can them be connected? Look here. See, we have studied delta G is equal to delta H minus T delta S, haven't we? Yes. We have also studied delta G is equal to minus T to minus 2.03 RT log K. That also we have studied, isn't it? Then you can avoid delta G and you take this part along. Delta G is equal to delta H minus delta G avoid delta H minus T delta S is equal to minus 2.03 RT log K. It has delta H is there, log K, so K is there, delta S is there, T is given, R we know. So we can substitute. See, delta H given 666 kilojoule minus T 60 degrees Celsius 273 plus 60. Delta S has to be found out, minus 2.03 into R in kilojoule, 008314 instead of 8.314, okay, in kilojoule, and T again 273 plus 60 into log D by N, denatured form by original form, okay. But in the question it is said that their constant denatured form and the original form of protein have same concentration. So log D by N means log 1 is equal to 0. So the whole right hand side becomes 0. Isn't it? 666 minus, this is 333. 333 delta S is this equal to 0. So the calculation become very easy. 666, this is equal to 0. So 666 is equal to 333 delta S. So delta S 666 divided by 333 is equal to 2. So correct option among the given 2 kilojoule per mole per Kelvin. Okay. So even though by reading the question one may get confused, but if you know the proper equations and apply them correctly, you are going to get the answer very easily. Okay. Right. Question is a matching type. On the left hand side column you have formula PCl5, BrF5, BF4 minus, NiCN for 2 minus. On the other side you have tetrahedral, square planar, trigonal bipyramidal, square bipyramidal. If you are already familiar with all this, you can easily correlate or easily cross match. Otherwise you will have to think detail, isn't it? Okay. You will see that how to verify. First PCl5. First you have to write the ground state electronic, valence state ground state electronic configuration of phosphorus. 3s2, 3p3. Isn't it? A pair of electron and a 3 unpaired electron. And valence is your P in the excited state. See, in PCl5 we know that there are 5 single bonds, covalent bonds, isn't it? So there must be 5 unpaired electron in the structure formula or in the atom. So you have to think about exciting the electron. So we see what happens. 3s2, actually it becomes 3s1 because this electron get promoted to the vacant d orbital. Then the new electronic configuration, there is a mistake, it is not 3s2, 3s1, 3s1, 3p3, 3d1, 3s1, 3p3, 3d1. These 5 electrons in the 5 orbital undergo sp3 dehybridization. These 5 half-filled undergo sp3 dehybridization, and we know the regular geometry of sp3d, it is trigonal bipyramidal, isn't it? So PCl5 takes the shape trigonal bipyramidal like this. Okay, PCl5 trigonal bipyramidal. So we have explained the PCl5. We proceed to the next. BRF5. Okay, listen carefully. First, think about the ground state electronic configuration of bromine. It is 4s2 bromine, now one more electron for completing the octet. So 4p5, 2, 2, 1, isn't it? And there is only one unpaired electron. So presently it can form only one covalent bond. But in BRF5 there are 5 covalent bonds. So 2 more pairs have to get unpaired. 2 more pairs have to get unpaired so that present one unpaired electron become 5 unpaired electron. So 2 more get unpaired. You can take them from 4p. So what happens after excitation? The new electronic configuration 4s2, 4p3. There are mistakes in the, actually it is 4p3 and 4d2. 4s1, don't look at this, they are mistaken. 4s2, 4p3 because d2 get unpaired into the next d level, 4d2. Okay, 4s2, 4p3, 4d2. Now these 3 plus 4 plus 5 plus 6 orbitals undergo sp3d2 hybridization. sp3d2 hybridization. See, out of this sp3, we know what is the regular geometry of sp3d2 hybridization. It is octahedral, isn't it? But remember, in this case, one of the sp3d2 hybridized orbital has a pair of electrons. This one, this is a pair, no? So in the structure, out of the 6 sp3d2 hybrid orbital, one will have a lone pair of electron. One will have a lone pair of electron. And while we consider the shape, when the structure is considered, listen carefully, when the structure is considered, structure is also called electron pair geometry. When the structure is considered, we have to consider the lone pair also. Then it will be distorted octahedral. Instead of fluorine, we have one orbital containing lone pair. So there will be slight distortion to the remaining part of the molecule. So it will be distorted octahedral. And what is the shape? Shape means molecular geometry. Structure is electron pair geometry, which contains the lone pair of electron. Shape is molecular geometry. It contains only molecular part, not the lone electron pair. It avoids the lone electron pair. Then what remains? If you ignore this balloon, what remains? Square pyramidal. So BRF5 will have the molecular geometry, or otherwise called shape, is what, as I told you, square pyramidal. See, it is not proper to give simply geometry. Geometry can be either electron pair geometry or molecular geometry. They must specify whether it is molecular geometry or electron pair geometry. Here, electron pair geometry is distorted octahedral and shape is square planar. Okay. Not square planar, square pyramidal. I am sorry. Next, BF4 minus ion. First thing about the valence configuration of boron. 1s2, 2s2, 2p1. 5 electron total. 1s2 inner shell, 2s2, 2p1. So 3 valence electron. If it get excited to this pair get excited over there. So 2s1, 2p2. It becomes 2s1, 2p2. Don't, these numbers are wrong. 2s1, 2p2. In BF4 minus, see, it can now it has 3 unpaired electron, and BF3 it can be easily formed by undergoing sp2 hybridization. If it undergoes sp2 hybridization, it will have a trigonal planar geometry, and the 3 BF bonds are formed in the same plane, so the molecular geometry will be BFO. What happens when another F minus comes? It make use of one of the vacant p orbital. Here there is a vacant p orbital into which the fourth fluoride coordinates. Then BF3 plus F minus become BF4 minus. Then the trigonal planar geometry changes to tetrahedral geometry. Hybridization also changes from sp2 to sp3. You can imagine this way. First BF3 is formed through sp2. 1 s electron, 2 p electron, sp2 hybridization. BF3 trigonal planar is formed. Thereafter, one more fluoride comes in to accommodate its lone pair of electron. Vacant orbital is made use. Then the hybridization changes from sp2 to sp3, and the molecular and the geometry of the molecule changes from trigonal planar to tetrahedral. Once BF4 minus is formed, you cannot say which was the last fluoride came. All will be identical. It will be very much similar to methane molecule. Okay, all bonds become identical. You cannot say this is the last fluoride came. No, you cannot say that. Okay, like this BF4 minus ion. Similar structure to CH4. CH4 doesn't have a charge, but BF4 has a minus charge. That's the difference. Now NaCN4, 2 minus NaCN4. So first you have to think about the valence electronic configuration of nickel. Nickel 4s2, it has no p electron, 3d8. 4s2, 3d8. After cobalt comes nickel. So it has one more electron than cobalt, which is 27 for cobalt, so 28. And its valence configuration, you have to remember, 4s2, 3d8, so 3 are paired, 2 unpaired electrons are there, isn't it? See, NaCN, you know, cyanide is a strong ligand, no? So it can pair up these electrons. So when it pair up these electrons, one vacancy will be created, no? Isn't it? One vacancy will be created. It is not shown here. This again, one vacancy will be created here because these two get paired up. So one d orbital become available. Okay. Before one thing I'm sorry, one thing I forgot. In NaCN for 2 minus, cyanide has a total of 4 minus charges. Cyanide has a total of 4 minus charges. But only 2 minus charges are remaining in the complex ion as a whole. That means nickel is having +2 charge. Nickel is having +2 charge means before forming this complex, nickel ionizes, releasing these 2 electrons. Okay, releasing these 2 electrons. So valence electronic configuration of Ni2 plus 4s0, nothing is remaining, and 3d8. Agreed. 3d8. Now it think about pairing because cyanide is a strong ligand. It get paired up. Okay. What I say is printed here. You don't have to worry what it is. Okay. Then what comes here? A vacant d orbital appears, isn't it? S is already vacant because it has been ionized. So S is there, D is there, P is totally vacant. 3 p orbitals are already vacant. Thus they are not shown. So it can easily undergo d-sp2 hybridization. Agreed. D made vacant. S is already vacant. P is ever vacant. So d-sp2 hybridization it undergoes. And we know the regular geometry of d-sp2 is coplanar. Like this. Nickel 4 cyanide group all around. Square planar model with the 2 minus charges. About all this properly cross-matched. I am not going back to the question. All this cross-matched together is 2. Option 2 is the answer for this question. Okay. See, the next question is regarding addition of certain molecules to double bonds in a molecule. See, addition can happen to a alkene which has either cis structure or trans structure. Okay, one thing. And the other thing, the way of addition, the mechanism of addition can be syn or anti. What are syn and anti? See, imagine a molecule with a double bond in this plane. In one case, both the atoms attached to the molecule from the same side. Double bond from the same side. This carbon and that carbon. From the same side it get attached. That is called a syn addition. In certain other cases, addition happens. In one carbon, it attached from this side, whereas in the other atom, it get attached from the opposite side. That kind of addition from opposite side is called anti-addition. Okay? One addition both from the same side. Other case, addition from opposite side. Syn and anti. That you remember. So, we will have to consider altogether 4 cases. What are they? To addition of cis type alkene. Cis alkene, where addition can be syn, where addition can be anti. Second, trans, where addition can be syn, addition can be anti. So, we consider 4 additions. Okay. And for simplicity, we are taking but2ene. But2ene. See, what is the specialty of but2ene? Imagine but2ene structure plane of the molecule. You have 2 CS3 and 2 H on the double bond, isn't it? On each carbon there is 1 CS3, 1 H. 1 CS3, 1 H. Okay. And suppose bromine is or halogen is attaching. So, the 2 new atoms attached also are the same. Agreed. XX, isn't it? So, after addition, both the carbon will have CH3, H and X atoms. Agreed? Isn't it? After whatever be the way of addition. After addition, each carbon will have 1 CH3, 1 H that were already present, and thirdly, a new atom attached, which is X, halogen. So, then, after addition, the product can have 2 different kind of structure. See, in one case, listen carefully. In one case, suppose this is hydrogen. So, yellow is hydrogen. One hydrogen on one carbon is just in line or in plane with the hydrogen and the other, above and below. If you hold the molecule like this, hydrogen above hydrogen. Then, halogen above halogen. Then methyl about methyl. That is, if you hold, I will make clear, if you hold one atom in one carbon just above the same atom on the other carbon, the remaining 2 atoms are remaining 2 group also get identically aligned. When yellow is aligned in this, as per this model, when yellow is aligned with the yellow, green is aligned with the green, and the red is aligned with the red. Such molecules are called erythro. Even though that name you don't have to remember, other details you have to remember. Because the next question will prove that you have to remember these things. Okay. So, remember, even though name is not must to remember, but better remember. Erythro. Erythro means similar group above and below. Okay, in one case. The other possibility is that, again when hydrogen is above hydrogen, the other 2 get cross-aligned. Here all the 3 are identically aligned. In this structure, all the 3 are identically aligned, whereas in this structure, they are not identically aligned. How? When yellow is aligned with yellow, when you can rotate them, there is free rotation. And when you brought this yellow just above yellow, red happens to be above green, and green happens to be above red. In this case also free rotation is possible. If you hold this molecule like this and brought yellow above yellow, red will be above red and green will be above green. And this type is called erythro, whereas this type, cross-aligned type, is called a trio. So please remember these 2 names. Erythro, all the 3 identically aligned. Trio, when cross-aligned. Erythro, ERY, THRO, THRE, EO, trio. THREO, trio. Erythro, trio. Please remember that. Now I told you, our case of study is but 2A with already CS3H and CS3H on 2 carbon. No? Now, suppose bromine, listen carefully. Let this be, I will start with the cis model. See, when let green be hydrogen and red be CS3. Okay, when let green be, listen carefully, when green is hydrogen and red is methyl, if it is cis2-butene, and suppose the attaching group comes from the same side and attach like this, on the same side if it attach, what you get is erythro, isn't it? Got that? I repeat. When greens are on both green are on the same side, both reds are on the same side, means it is what? This was the original molecule. And after addition of two similar group, from syn addition, you got this erythro. Now, can't you say that syn addition on cis gives erythro? Agreed? Syn, that is from same side. Addition to cis gives erythro. Syn addition to cis give erythro. Agreed? Okay. On the other hand, if one yellow comes from this side and other yellow comes from behind, I repeat, one yellow comes from here, other yellow comes from here, back. So this yellow is in front of you. This yellow you cannot see because it is behind. So you please rotate it and bring that yellow in front of you. Okay. Then red will be in line with the green and green will be in line with the red. Isn't it? Think about it. I repeat, again listen carefully. Here one yellow comes from here, other yellow comes from behind. So this yellow you immediately see, this yellow you cannot see. So you rotate this end along because free rotation is possible and brought that yellow in front of you like this. Then what will happen? Here when yellow aligned with the yellow, red aligned with the green, green aligned with the red. Isn't it? Okay? Great. I hope you understood that. You started from this, but addition is anti. Yellow came here in front, yellow came here back. But so you can immediately see this yellow, but you cannot see this yellow. So you rotated, free rotation is possible. You brought this yellow in front so that you can see that. Then what happened? The red below comes to upper and this green above will come down. Then the structure obtained will be like this. So what is your conclusion? Anti-addition to cis give you erythro. Trio. Agreed. Anti-addition to cis give you trio. This is trio, no? When all the three are identically aligned, it is erythro. When there is cross alignment, it is trio. I repeat, when all the three are identically aligned, it is erythro. When they are not identically aligned, only one is aligned, whereas the other two are cross aligned, it is trio. Okay, that you remember. Then I told you, syn addition to cis give you all identically aligned. Syn addition to cis give you all identically aligned means you get erythro. Anti-addition to the same cis give you trio because they are cross-aligned like this. You have these figures in your mind and think. You will get the same conclusion. Slowly think. Okay, so now you got, listen carefully. Both these are obtained from cis. I repeat, both these are obtained from the cis type molecule. This is through syn type addition. This is through trans type addition. This is through syn type addition. This is through trans type addition. I'm anti-type, trans type, no, I'm sorry for using the wrong word. Anti-addition. Syn addition, anti-addition. Syn addition on cis, anti-addition on cis. Agreed? This is all identically aligned erythro. This is only one identically aligned, whereas the other two are cross-aligned are trio. You make your own chart and make by heart. We have covered only the cis part. Now we come to the addition of trans. Agreed? Okay. I take a break. Now I took the trans form of butadiene, trans butadiene. Agreed? And now first, as in the previous case, syn addition. Think that one yellow is attached in front and the other yellow attached here in front. Both in front. Agreed? Then you will get this molecule. Agreed? You will get this molecule. This on syn addition will give this. Agreed? Both are attached on the front like this. Agreed? This was the original molecule. This is after syn addition. What is it? Trio. Because only one is aligned. Agreed? Right now? Slowly think. Or make your own diagram and think. Once it is gone into your mind, you will not forget. Okay? Now, anti-addition. Okay? First, this is trans versus anti-addition. One yellow goes over this. Agreed? The other yellow goes over this. You can see this yellow, but you cannot see this yellow. So you turned it 180 so that yellow comes in front of you. Then what happened? It became erythro. Green, all the three will be aligned. Isn't it? Isn't it? This is trans, no? If it undergoes syn addition, you have only one aligned, two unaligned, not aligned. So it is trio. On the other hand, if it is one attached here, other attached from the opposite side, it is anti-addition, no? So to make things more clear, you rotated one end so that both yellow came to you in front of you. Then yellow is with the yellow, green is with the green, red is with the red. It is erythro. So I say that, listen carefully. When trans form add, listen carefully, when trans form adds syn way, trans form adds syn way, that is from the same side. You have only one aligned, that is trio. Transform anti-added, you get all the three aligned erythro. So both give erythro and trio. In one case, syn addition give erythro, the other addition give trio. In the other case, syn addition give trio, the other give erythro. So there are only two products, erythro and trio. It is very easy to remember. Cis versus syn. Very easy to remember. Cis versus syn, all the three aligned, erythro. Cis versus anti, only one aligned, trio. Okay. Now trans. Trans versus syn, trio. Trans versus anti, erythro. It is very much similar to plus into plus is equal to plus, minus into minus is equal to plus, plus into minus is equal to minus, minus into plus is equal to minus. How you can connect these two? Make your own chart. Cis versus syn is plus into plus. Cis versus syn is equal to plus into plus. Gives erythro is the plus on the other side. Erythro. Cis versus syn, erythro plus. So erythro is plus, trio is minus. Okay. So cis versus syn and trans versus anti, that is negative into negative. Trans is a negative connection. Anti-addition is a negative connection. But that gives you same erythro. Cis versus syn, erythro. Positive into positive, positive. Trans versus anti, effect cancels. Again erythro. Agreed. Already cross and attachment is cross. So it become erythro. All the three get aligned. Okay. Again, negative into plus and plus into negative. What are they? Both giving negative. Cis anti-addition, trans syn addition. Cis anti-addition, trans syn addition, both gives you trio. Okay, that is plus into minus negative, minus into plus negative. Now you make your own chart and make all these things by heart. Okay, I think that is sufficient. If you didn't follow well, repeat this part. See it again. Okay. As I told you, cis versus syn addition and trans versus anti-addition gives erythro product. Remember, plus into plus as well as minus into minus plus. Another point, cis versus anti-addition and trans versus syn addition both give trio. Remember, plus into minus as well as minus into plus minus. Okay. We are going to apply that to the question. Statement 1. Trans but 2-ene upon treatment with the bromine in CCl4 gives the following product. A structure is given. It is Newman's projection formula. Okay. Statement 2. Cis but 2-ene upon treatment with the alkaline KMnO4 gives the following product. Newman's projection formula. Another product. In the light of the above statement, choose the most appropriate answer. As usual, that is as usual, both statement correct, both statement incorrect, statement 1 alone correct, statement 2 alone correct. We will check that. Okay. Now listen. Some information. Listen carefully before looking there. All catalytic addition are syn addition. Remember, because catalyst surface, alkene comes to stay above it. Catalyst surface hold either hydrogen molecule or halogen molecule on the surface, and HH bond weakens or excess bond weakens. Then each atom directly get attached to the double bond. So addition happens from the same side of the double bonded molecule. Double bonded molecule is laid like this, not like this, laid above the surface of the catalyst like this. Then addition happens from the same side. So all catalytic addition is syn addition. Remember this point. On the other hand, if you are adding halogen from CCl4 medium or aqueous medium, either from CCl4 medium or aqueous medium, addition is always anti. In liquid medium, halogen addition is anti. That is, one bromine get attached from one side as Br plus and other side as Br minus. Br minus plus Br plus is Br2. So in effect addition is Br2, but as Br plus and Br minus, that happens from opposite side, anti-addition. So halogen from halogen or hydrogen in a catalytic media, catalytic addition happens always syn, but in a liquid medium, halogen addition is anti-addition. Then another reaction is hydroxylation. Bayer's test. How you test for unsaturation? You add cold dilute KMnO4 or mildly alkaline KMnO4. Hydroxylation takes place. In the place of double bond, 2 OH group comes into the double bonds position, making it a single bond with the 2 OH attached. That is why it is called a hydroxylation. Hydroxyl groups are attached to both the atoms. That is always from the same side. Syn addition. So catalytic addition, so remember catalytic addition and hydroxylation of double bond, they are syn. Whereas halogen addition in a liquid medium is anti. Keep that in mind. Okay. Now, what is the first case here? To transmute toluene, anti-bromine is added in CCl4 medium. Bromine is added from CCl4 medium. So, our addition is to trans addition is anti. Trans addition method anti. Negative into negative positive. We have studied. We are supposed to get erythro. All the 3 groups identically aligned. We will check then whether the given product is having erythro structure. See, this structure is not required here. Still I am telling that. See, if bromine is adding from the front here, so it will be staying like this, isn't it? It will be having an angular towards the viewer, slightly towards the viewer. That's why I have shown this bromine with a solid line towards the observer, slightly towards the, partially towards the observer. To accommodate that bromine, the 2 CS3 and H in the plane of the board slightly goes backward. Okay? Slightly goes backward. So, the whole arrangement will be like this. Bromine towards the viewer, somewhat towards the viewer, whereas the CS3 and H slightly away from the viewer. On the other side, bromine attached from the rear side. So, I have shown that by dash lines. Okay, dash lines. So, H and CS3 come towards the viewer. Okay, isn't it? So, H and CS3 is shown by solid line, Br by dash line. Here CS3 and H by dash line, Br by solid line. See, this structure has to be converted to this structure. This structure is converted to this structure. How? Listen, actually, we can forget this. We don't actually require this structure to get the answer. We just want to know whether the shown product is anti or syn. That is sufficient. Why should we waste time? Even though, if at all in some question, some diagram like this is given and asked, you must be able. That's why I explained that. That's all. Okay. Now, for this particular question, we directly enter into this question. Okay. See, this given structure is this. Is this syn or anti? To understand this, imagine this we can rotate either the front bromine or the back. Let's rotate the backward. Bring this bromine to this position. Rotating, bring this bromine to this position. Then it is moved through 180 degree. No, this bottom bromine, when brought behind the bromine, it has been rotated through 180 degree. So methyl also get rotated through 180. So this methyl will come behind H. This H will come behind B, Me. When bromine is when you try to align bromine with the bromine, hydrogen get aligned with the methyl and methyl get aligned with the hydrogen. You didn't get what? Erythro. You got a trio. Actually, we have in this particular case, anti-addition to trans. We know by our rule, and trans versus anti must give erythro, all the 3 aligned. Whereas the given Newman projection formulae suggest the product to be 3O. That's why I told you, even though names are not in the syllabus, it is better that if we name it, we can easily call it. That's why I ask you to learn the names. So we expect erythro, we got 3O. How we can say that we got 3O? You rotate the rear side carbon through 180 degree. So bromine comes behind the front bromine. But hydrogen goes behind methyl and methyl goes behind this front hydrogen. So 3O, only one is aligned. The other two are cross aligned. So other two are cross aligned. No. So we got 3O instead of erythro. The first statement is wrong. They have given this structure. So the first statement is wrong. Okay. Now we proceed to the second statement. Look. The second case, what it is? Cis-but-2-ene. Cis-but-2-ene. Okay. And I told you KMN of our alkali syn hydroxylation, syn addition. Cis versus syn. Again it should be erythro. Isn't it? Actually in our question both reactions lead to erythro. And we will now check whether the given structure is erythro or 3O. This is the given structure here. Arrow, look at the direction. This is the arrow. So in the question paper the given structure is this. Is it erythro? How to check? Bring this OH to this behind this OH by rotating to 60 degree. Only 60 degree rotation is needed. So what happened? When this is rotated to this behind this, Me will come behind Me. H will come behind H. Every three aligned. So it is erythro. Actually we expect erythro because it is cis versus syn. Cis versus syn is erythro. The given structure is erythro. The second statement is correct. So we got the answer. The first statement is wrong. The second statement is correct. Okay, that is the answer for this question. 4. I think option 4 is the answer. Okay, so we have finished that. Yeah, option 4 is the answer. Okay, if you by listening for one time, if you didn't get it, please go through it repeatedly, 2-3 times. Okay, it is a bit troubling, especially since it involves more imagination in space. Okay.